Good morning to one and all. Good morning. So as we said yesterday, first we are going to think about uh, definition of the Y bus elements and then definition of the Z bus elements. Yeah. So I'm taking up in the next slide, that is definition of Y bus elements. Definition of Y bus elements. See, as you know, relationship between the bus voltage vector and bus current injection vector, we have discussed already in the view of Y bus. That is, bus current injection vector is equals to bus admittance matrix into V bus. Bus admittance matrix into V bus, you can say. So if it's a N bus system, you have written this is of N by 1 size, N by N size, and it will be again of N by 1 size, right? I bus equals to Y bus into V bus here. Okay, next thing. Let us expand this matrix little bit. I will be expanding this matrix in the way of N by N matrix here. So I bus I am going to call like I1, I2 and so on up to II and so on up to IN. Like this will have bus current injection vector I1, I2 and so on up to IN. So here you get the Y bus matrix. I'll keep that Y bus matrix for time being. Next V bus matrix you see V1, V2, so on up to Vi and so on up to Vn. These are bus voltages at these N nodes. Yeah, please kindly observe my words. Whatever the Y bus elements we have here, Y bus elements, I will be indicating these elements with capital letters. Y bus elements I will be indicating with capital letters like capital Y11, capital Y12, capital Y13, and so on. Capital Y1I and so on. Capital Y1N, like this. And whereas the second row you can call capital Y21, capital Y22, capital Y2I and so on up to Y2N. Next, ith one, capital YI1, capital YI2, YI2 and so on, capital YII, so on up to capital YIN, like this. And nth row, if you think here, N1, N2, Ni and so on up to Nn. Like this, we'll get the Y bus elements. Yeah, please be clear about this terminology. Capital Y, if I am using the symbol, you also have to follow this terminology properly in your notes or in your what we call problem solving, wherever it is. Capital Y anywhere you see like this, that is a Y bus element. Capital Y is a Y bus element. What is small y? Small y, for example, you see in the network what I have shown here, I have taken up the elements like small y10, small y20, small y30, small y12, small y23. And the small y what I have shown here, it's an indication or it's a notation for admittance of a branch. Maybe it's a series branch or shunt branch, whatever it is. Else, you can say in a more flexible way or more appropriate way, it is going to be called as primitive admittance of the branch. Okay. So I will be showing small y here. It is called as primitive admittance of the branch. Primitive admittance of the branch that we are denoting with a letter small y. Primitive admittance of the branch. Okay, next thing. Simple, very simple thing. Just write this II equation, ith bus current injection equation. We can take that matrix multiplication. Yi1 V1 plus Yi2 V2 plus and so on. Yii Vi plus and so on. Yin Vn. Like that you can write. Let me write that current injection. Ith bus current injection I am writing. II equals to, from matrix multiplication, Yi1 V1 plus Yi2 V2 so on Yii Vi So on yin vn. Like this, we can write the ith bus current injection equation, II. A very simple question I am asking you here. Very simple question. What is the element yi2? How to calculate that element yi2? How to calculate that element yi2? Very simple. Make all the voltages 0 except V2. You keep V2 non-zero number. Keep remaining all voltages as 0. By doing that, you can get this II equals to yi2 into V2. Then yi2 is nothing but II by V2, we can say. It's a ratio between ith bus current to bus 2 voltage, by making all other remaining bus voltages as 0. K equals to 1, 3, 4, 5, and so on up to n. K should not be equals to 2. K should not be equals to 2. This is a way of calculating yi2 number. yi2 number, II by V2. We should keep some voltage at bus 2 as V2 number, and we should keep 0 voltage. Listen my words. We should keep 0 voltage at all other remaining buses, right? And then you have to calculate the ratio that is going to be called as capital YI. What is the value capital YI now? In a similar way, what will be the value capital YI? It will be ith bus current injection to the ith bus voltage by making all other remaining voltages as 0. So K value will be 1, 2, 3, and so on up to n. K should not be equals to I. K should not be equals to I. Ith bus current injection to ith bus voltage. This ratio we should take by keeping all remaining voltages as 0. So Vk equals 0. K equals to 1, 2, 3, and so on up to n. K should not be equals to I. Okay, simple. What will be the name given for these elements? That we have to think. What will be the name given for these elements? Of course, these are admittances. Sure, admittances. See, generally in the network theory terminology, if you take ratio between current in one port, voltage in the other port, it's a n port network. It's a n port network. Okay, we are taking current in one port, voltage in the other port. That ratio is going to be called generally as transfer value. It's going to be called as generally transfer value. So particularly I will name it as now transfer admittance of the network. Okay. Whereas this one, II by VI. This we are going to name as driving point admittance. Okay. See, these Y bus elements are transfer admittances and driving point admittances. Okay. How you are calculating them? By making remaining bus voltage as 0. Making remaining bus voltage as 0 means obviously we have to make a short circuit. So these are nothing but simply short circuit, driving point, and transfer admittances of the network. Okay. Yeah. So let me define in a separate way. First, I will say off diagonal elements here. First, I'll say off diagonal elements. Off diagonals of Y bus. Off diagonal elements of Y bus. These are nothing but short circuit, transfer admittances. Short circuit transfer admittance of the network. Whereas diagonal elements of Y bus, these are nothing but short circuit driving point admittances. Short circuit driving point admittances. So just how I have explained you, right? So just if you look at this matrix, if you want, look at this matrix. Let me take up this diagonal, Y11, Y22, Y33, and so on up to YII, and so on up to YN. These are the diagonal elements, right? These diagonal elements I am going to call as short circuit driving point admittances. Whatever the off diagonals you have in the upper and lower, these off diagonal elements we are going to call as short circuit transfer admittances. Clear? Right. Next thing. Very simple question I am asking you, very, very simple question. Which are excitations and which are responses in this matrix? Which are excitations and which are responses in this matrix? Simple, I'll tell you in the calculation of yi2, we have to keep a voltage source of V2 at bus 2. We have to keep a voltage source of V2 at bus 2, and we should keep zero voltage source at all other remaining buses. Zero voltage source at all other remaining buses, and we have to calculate the ith bus current injection to the bus 2 voltage source what you kept, that we are calling as yi. Means which value we are calculating? Current you are calculating by keeping what? Voltage. So obviously voltage what you are keeping here, that is the excitation. Current what you are calculating here, that's a response. So I can say here voltages V1, V2 and so on up to Vn, these are going to be called as excitations. And these currents what we have here, these are going to be called as responses. Currents are going to be called as responses, voltages are going to be called as excitations. So simple, this is the definition of the Y bus element, Y bus matrix or Y bus elements you can say. So let me take up the Z bus elements definition also quickly. Definition of the Z bus elements. So I'm moving to the next slide. Definition of Z bus elements. Definition of Z bus elements. Yeah, let me write up that matrix of N bus system here. N bus system matrix you write. So bus voltage vector is equals to bus impedance matrix into bus current injection vector. Bus voltage vector equals to bus impedance matrix into bus current injection vector. And if it's a N bus system, you can write bus voltage vector N by 1, Z bus N by N, bus current injection N by 1. Write the elements in the matrix form. Bus voltage vector, you'll get like V1, V2 and so on, Vi and so on up to Vn. Like this, you will get the bus voltages. V1, V2 and so on up to Vn. Okay, Z bus matrix. And then this bus current injections, calling as I1, I2 and so on up to II, so on In. Like this, we'll have bus current injections. Let me denote again these Z bus element symbols. Z bus element symbols I am writing now. I'll say it is Z11, Z12 and so on up to Z1I and so on Z1N. Okay, these are Z bus elements of the first row. Second row, 21, 22, 2I and so on up to 2N. Yeah, and if you take up that ith row, Zi1, Zi2, so on, Zii and so on up to Zin. And nth row if you take up here, N1, N2, Ni, so on Nn. Like this you will get. Like this we are going to get the Z bus matrix. Okay, done. Now again, in the similar way of Y bus elements discussion, here also you write what is that ith bus voltage, Vi. That is nothing but Zi1 I1 plus Zi2 I2 plus and so on Zii II plus and so on up to Zin In. Like that you write first. After that we will take it. So let's take up that ith bus voltage Vi. Ith bus voltage Vi. Zi1 I1. Zi2 I2. So on Zii II. And so on Zin In. Zin In. Like this. Now you try to write what is this Zi2 number? What is a Zi2 number here? In the similar way, Zi2 number means we should keep all current sources 0. All currents at 0 except I2 number. We keep I2 number, take the ratio between ith bus voltage to second bus current. ith bus voltage to second bus current by keeping remaining currents as 0. So the K value was 1, 2, 3. 2 we have to remove. 3, 4, 5, and so on up to N. And the K should not be equals to 2 here. K should not be equals to. So ith bus voltage to second bus current injection. Second bus current injection we should take. And what is the number ZII we can write here? What is that number ZII? It is a ratio between ith bus voltage to ith bus current. Ith bus voltage to ith bus current by keeping all other currents as 0. So K equals to, sorry, 1, 2, and so on up to N, where K should not be equals to I. K should not be equals to I. Okay, very simple term again, very simple term and simple extension to the previous discussion what we have made. So what is this ratio we can call? Ith bus voltage to second bus current. Na? Anybody please tell me? Please tell me quickly. Ith bus voltage, we are measuring voltage in one port. You keep the current at some other port. What is this ratio we are going to call? Transfer impedance. It's going to be called as transfer impedance. Okay. Transfer impedance, how you are calculating? By keeping remaining currents as 0. Transfer impedance you are calculating by keeping remaining currents as 0. Means by making open circuits. So it is going to be called as open circuit transfer impedance of the network. Okay. And this is going to be called as driving point impedance. Particularly, we can say open circuit driving point impedance. So I'll write here. So I'm writing here. Off diagonal elements of Z bus. Off diagonals of Z bus. Okay, these are nothing but open circuit transfer impedances. Transfer impedances. Open circuit transfer impedances. Okay, and diagonal elements of the Z bus. Diagonal elements of Z bus. Elements of Z bus. These are nothing but what? Open circuit driving point impedances. Open circuit driving point impedances. Driving point impedances. Simple. Simple terminology we have taken. So in the previous slide where we have shown the Z bus elements, you can observe now Z11, Z22, and so on up to Zn. These are the diagonal elements of the Z bus. Diagonal elements of the Z bus. What is the name we are giving for these diagonal elements? These are nothing but open circuit driving point impedances. Open circuit driving point impedances. And these off diagonal elements we are going to name as open circuit transfer impedances. That's what the definition what we have made till now. Okay. So in a simple understanding, if you want, you can feel that Y bus elements, whatever you are calculating now, are nothing but Y parameters in the network analysis. Y bus elements are nothing but Y parameters in the network analysis. But in network analysis, you calculate the Y parameters only for a two-port network. Two-port network. But here we are discussing that in the view of N buses or N ports. That's it. That's only the difference. Clear? Similarly, Z parameters you might have calculated in your network analysis, right? And in the similar way, we are doing the Z bus also. So Z bus parameters are equivalent to the Z parameters. Y bus elements are equivalent to the Y parameters. But only one change what we are experiencing here is we are discussing with respect to N bus system or N port system. Okay? Yeah. So fine. So I think all of you getting the definitions of these two elements. Now let's move to one simple problem in the view of this Z bus and Y bus elements calculation. In the view of the Z bus and Y bus elements calculation. Yeah, please raise your hands if you have completed. Okay, good. So let's take up this question. See this one. Observe this. Consider the following single line diagram with all reactances of apparatus given in per unit form. Find Y33 and Z33 of the Y bus and Z bus matrices respectively. You have to find out the values of capital Y33 and capital Z33. These two elements you have to calculate in the Y bus and the Z bus. Okay, listen here. Stop writing. Just listen to me. How you will be representing each and every element in the Y bus and Z bus construction, that we have to discuss first. Already I said, I think for generator. How you represent generator? Current source in parallel with its internal impedance. Yes or no? Transformer, series impedance. Okay. Line, series impedance. Okay. How you represent load in the Y bus and Z bus construction? How you represent the load in the Y bus and Z bus construction? It is going to be represented as current injection. Maybe it's a negative current injection, whatever it is. Okay. So first I will write that statement because I have not discussed about the load representation in the previous class, right? First, let me write regarding that load. Load represented as current injection. Current injection in Y bus construction. In the Y bus or Z bus, whatever it is. Y bus or Z bus construction. Means my intention is to tell you, for example, if it is a load indicated in the single line diagram, this is going to be taken as current injection, something like this. But this current may be a negative current, as I said. This current may be a negative current, right? Current injection. Now, listen all of you. So as a first step in the calculation of the Y bus and Z bus elements, first you replace the single line diagram given with its equivalent model. Okay. After that, we will see what we have to do further. So I'll say in the next slide, the per phase network of given single line diagram. Per phase network of given single line diagram. First, generator. Generator means it is represented as a current source in parallel with internal impedance. Right? You call it is ZG, and this is a current source. I am showing IG. Yeah, any load it's going to be represented as current injection right now. That's it. Next thing. After that, this is a bus 1. Okay, bus 1 to bus 2, we have a transformer. Let me show that element. Bus 2, it is a ZT transformer impedance. Next, you have bus 2 to bus 3, you have a line. So it's a bus 3. And between bus 2 and bus 3, we have an element of ZL, you can say, ZL. And then at the end, at the bus 3, what you have? Load. Load in the sense you are going to represent that load with a current injection negative L. Current injection negative L. Like this we can say. Okay, next thing. Class will quickly. Numbers, ZG is J0.3, ZT J0.2, ZL J0.1. Like that, we'll keep the numbers in the next slide. Listen kindly. See, after drawing this network, immediately in the next step, what you have to do is, we have to take up the network by removing the sources existing. By removing the current sources, whatever you have, you take only the network of impedances. Take only network of impedances. Sometimes it can be called as primitive impedance network. Primitive impedance network. Don't confuse. Primitive impedance network is nothing but simply representing the given single line diagram into its electrical equivalent circuit. That itself is going to be called as primitive impedance network. That's it. Okay. So let me show in the next slide. Primitive impedance network. Primitive impedance network, or you can say network of impedances. It is bus 1, ZG, bus 1 to bus 2, ZT we have, Bus 2 to bus 3, ZL. Bus 2 to bus 3, it is ZL. Okay. Next. It's a reference. Last one is a reference which is operating at zero potential, of course. Zero potential. So now, first we have to calculate that value Y33. Capital Y33 calculation we have to do first. Capital Y33 calculation. What is the formula for capital Y33? What is the formula for capital Y33? Tell me please. It is a ratio between I3 to V3. I3 to V3 by keeping what? By keeping remaining bus voltages as 0. Or you can say by keeping remaining voltage source as 0. Remaining bus voltage sources as 0. Means bus 1 voltage source we should keep 0. Bus 2 voltage source also we should keep 0. And we have to keep some non-zero voltage source at the bus 3. And we have to find out the current injection into bus 3. And we have to take up the ratio. Clear? So let me copy this diagram. I will show whatever the thing I said till now in this diagram. Kindly observe. Yeah. So this one. So this is bus 3. And this is 0. Okay. Simple. Look here. Bus 1 voltage, we should keep 0 voltage source. So I'm showing like this. V1 is equals to 0 I made. Voltage source at bus 1 is 0. Means short circuit. Bus 2 voltage source 0 we should keep. So we should say V2 equals 0. But at bus 3 we should keep some voltage source. At bus 3 we should keep some voltage source. And I'm keeping it is plus minus V3. Plus minus V3. And current injection into that bus 3 we have to calculate, that is I3. Current injection into that bus 3 we have to calculate, that is I3. Yeah, all of you understood this? Please tell me. All of you understood this? I'm taking only impedance network. I no need to bother about these current sources. Whatever the existing current sources, you no need to bother about these existing current sources. Why? In the sense, simple reason I will tell you, these current sources I will take into IBus. These current sources I will take it into IBus. Whatever the YBus matrix you are going to construct now, that depends upon only network impedances and network admittances. It is independent on the current sources definitely. That's why I'm not considering the current sources existing. We are taking only network of impedances and we are doing the calculation of the YBus elements for that impedance network. Yeah, you please tell me, what is that current I3? Tell me please. This voltage is 0 already. So you can say current I3 is equals to V3 minus 0 by ZL. Simple. V3 minus 0 by ZL. And what is that I3 by V3 you can write? I3 by V3 number is 1 by ZL. 1 by ZL. What is the ZL value? What is the ZL value given in the data? J0.1. J0.1 we have to substitute. So I can call capital Y33 number is nothing but 1 by ZL here. So 1 by J0.1, this number will be minus J10 per unit. Minus J10 per unit. That's the value of capital Y33. Capital Y33. Simple. Okay. So this is a way of calculating capital Y33. Now let's move to Z33 calculation in the similar manner. Z33 calculation in the similar way. Z33 calculation. So let me copy the same impedance network as it is. Same impedance network I have copied here, this one. So bottom node, so-called reference 0 and it's a bus 3. Bus 3. See, Z33 we have to calculate. Z33. What is the formula for Z33? Z33 is a ratio between bus 3 voltage to bus 3 current. V3 by I3. By making what? Remaining currents as 0. By making remaining currents as 0. Remaining currents as 0 means I should keep 0 current source at bus 1. Listen to my words. 0 current source at bus 1. I should keep 0 current source at bus 2. and we should keep non-zero current source at bus 3. Listen, keeping zero current source at bus 2 means we have to keep an open circuit, right? We have to keep an open circuit. Yeah, this is a place where you should be very clear. Sir, in the earlier case, you said V1 0, V2 0. You made a short circuit. That's well and good. But how you are showing I1 0 here, I2 0? That's what I am saying. You kindly listen. I am not keeping any current source here. Not keep zero current source. I am keeping at this place. Means I will keep one current source at this place with zero current value. What is the meaning of that? It will be acting as open circuit only, right? Zero current source is nothing but simply open circuit, you can say. Okay? Zero current source is nothing but open circuit. Similarly, zero current source at bus 2, that's also open circuit. But you have to keep some current source at bus 3, naming this as I3. But you have to keep some non-zero current source at bus 3, that is I3. Now, by injecting the current, find out this bus voltage V3. Find out that bus voltage V3. Then, what is that I3 and V3 relationship you get? Based on that, you calculate the value of V3 by I3, that is Z3. Simple. So you can get here V3 is equals to I3 into summation of these three impedances. We should say ZG plus ZT plus ZL. ZG plus ZT plus ZL, you can say. So I3 into what is summation of these three impedances? Generator rating J0.3, transformer J0.2, line J0.1. It will come to be J0.6. Then you can get Z33 value simply. Z33 is nothing but the value V3 by I2 with the conditions what we have mentioned. This number will come as J0.6 per unit. J0.6 per unit. That's the value of Z33 number. Z33 number. Okay. So this is very, very basic technique of calculating the Z bus and the Y bus elements. Keeping excitations, finding the required voltages or currents, whatever you have, whatever you need, and you have to go with the elements. Okay, let's move ahead. For example, this was a single line diagram we have. Let's say this one. I'm copying this diagram. Single line diagram. Forget about the load for time being. Okay. For example, just listen. It's a single line diagram. Forget about this load for time being. Remove that load for time being. Listen. Simply in the examination, this single line diagram is given to you. Generator, transformer, line. Question is very simple. We have a three-phase short circuit fault at bus 3. Three-phase fault at bus 3. What is fault current? We have a three-phase fault at bus 3. What is fault current? For the formula for fault current here, that is nothing but pre-fault voltage by Thevenin equivalent impedance with respect to bus 3. Thevenin equivalent impedance with respect to bus 3 means should call this as Z3. Pre-fault voltage by Thevenin equivalent impedance with respect to bus 3 means you should call that as Z3. All of you getting this one? All of you getting this? Please tell me. Rather than Z33, as I am saying directly, if you feel, I'll say Z Thevenin with respect to bus 3, that's okay. Thevenin equivalent impedance with respect to bus 3. Please listen my words now. Pre-fault voltage by positive sequence Thevenin impedance is a fault current. That I have written. What do you mean by Z Thevenin 3 now? Z Thevenin with respect to bus 3 is what? And we have to draw this network generator with some representation, something like this. This is a generator. Okay. And you have a transformer series impedance, and you have a line series impedance, and you keep all these numbers here. This is J0.3, and this is J0.2, and this is J0.1. So with respect to bus 3, we have to find out the Z Thevenin value. How much is the Z Thevenin value with respect to bus 3? By killing the source, you have to get. By killing the source, you should get. What's the Z Thevenin value here? That is nothing but J0.6 per unit. Z Thevenin is nothing but J0.6 per unit. All of you getting this one? And this J0 points per unit, what you calculated Z Thevenin is nothing but the value of Z33, right? This Z Thevenin value, what you calculate here is nothing but Z33. Actually, listen. How to calculate Thevenin impedance with respect to a point? How to calculate Thevenin impedance with respect to a point? You should think in an exact way of network analysis here. In the exact way of network analysis, to calculate Z Thevenin with respect to one bus, we should kill all the sources existing first. We should kill all the sources existing. Then, with respect to what bus you want to calculate Thevenin impedance, at that bus, you keep one current source. Keep one current source. Find out voltage at that bus location. And you take up the ratio between voltage to current. That is what we call Z Thevenin calculation in the exact way. All of you understood this technique? Please tell me. I'm not getting any response. Have you understood this, what I said? Calculation of Z Thevenin exactly in the sense, with respect to what bus you want to calculate, that you decide first, and you keep a current source at that bus, take up the voltage to current ratio, that is a Z Thevenin value. That is nothing but the calculation of diagonal element, right? That is nothing but the calculation of the diagonal element of the Z bus. For example, you see in your Z bus definition, I've shown here, Z bus definition, how to calculate Z11? You should take voltage at bus 1 to current at bus 1 by keeping remaining current 0. How to calculate Z22? V2 by I2 by keeping remaining current 0. See, all these diagonal elements what we have written here. These are nothing but Thevenin impedances with the respective buses. And these impedances we will be using in the calculation of the fault current. So that I can say Z bus matrix will be used in the fault analysis. Okay. Yeah, I'll write that detailed statement. Kindly go through it. First conclusion I am saying. Conclusions. First one. Diagonal elements of Z bus. Diagonal elements of Z bus are Thevenin impedances. With the respective buses. Okay. Therefore, Z bus is used. In fault analysis. Z bus will be used in fault analysis. VPF is a pre-fault voltage. You calculate Thevenin, you have to do two calculations here. One, calculation of Thevenin voltage in a different way. Calculation of Thevenin impedance in a different way. Both values you can't calculate in a single attempt, right? Thevenin voltage and Thevenin impedance you can't calculate in a single attempt. We should do calculation of Thevenin impedance separately. We should do calculation of Thevenin voltage separately. How you are mingling these two again? Yeah, second one you see. Observe here, second one. See, actually, you have taken these Y bus elements here. You are getting Y33 is something like minus J10. And similarly, transfer admittances you have. Look once. See, already we discussed about power equation. I am repeating the power equation once. Kindly observe power equation. Power equation is P equals to something like mod E mod V by mod B. Mod E mod V by mod B cos of beta minus delta minus mod A by mod B mod V square cos of beta minus alpha. All of you remember this? Tell me. In the previous classes of stability analysis, we have discussed. Yes or no? Power equation EV by mod B into cos of beta minus delta minus mod A by mod B square cos of beta minus alpha. And what is the name of this parameter B? What is the name of this parameter B? It is going to be called generally as short circuit transfer impedance. Parameter B is going to be called as short circuit transfer impedance. It's going to be called as short circuit transfer impedance. Parameter B. Parameter B. Kindly observe the word. Observe the word. Short circuit transfer impedance is a parameter B. But just now we have discussed that Y-bus elements are short circuit calculations. Y-bus elements are short circuit calculations, but those are admittances. So short circuit transfer admittances we have calculated, those are Y-bus elements. Obviously, that inverse of the Y-bus elements we might be using in this what we call power equation. Or else we can say 1 by mod B. I will write here 1 by B. 1 by B is nothing but I am not changing the name. Short circuit only transfer admittance. Admittance. I didn't change the short circuit word. Short circuit calculation only. Previous one is the transfer impedance. Now I am saying that as transfer admittance. And this short circuit transfer admittance is nothing but Y-bus elements, which will come in the power equation. Which will come in the power equation. See, these power equations we will be using in the stability analysis. These power equations we will be using in the stability analysis. Just try to link up all these things. What is it? Power equation will come in terms of Y-bus elements. Power equations will come in terms of Y-bus elements. Okay. Power equations are used in stability analysis. So indirectly, in the stability analysis, we have to use a Y-bus elements. So Y-bus elements are used to do the stability analysis on the system. All of you getting these words? Tell me please. Yeah, I'll write these things. Kindly observe. Power equations will come in terms of Y-bus elements. Will come in terms of Y-bus elements. Okay, and stability analysis done by power equations, that implies for stability analysis, Y-bus elements will be used. Y-bus elements will be used. Y-bus elements will be used. Yeah. Y-bus elements will be used. This is one conclusion. Second conclusion. So this is the way how you have to understand where we will be using Y-bus matrix, where we will be using the Z-bus matrix, right? And the next conclusion, so-called third conclusion, I'm saying third conclusion. Just you can write from previous problem what we have done, previous problem. What is capital Y33 value got? What is capital Y33? Minus J10. Minus J10 is a value of capital Y33. What is capital Z33 you got? J0.6. Means you should understand this very clearly. If you take inverse of Y33, you don't get the value of Z33. If you take inverse of Y33, you don't get the value of Z33. Means I can say here, observe here, Z33 value is not equals to 1 by Y33 number. 1 by Y33 number. Or just to write these names. What is the name Z33? Please tell me, all of you. Please tell me, all of you. What is Z33 name? Name of Z33. Open circuit driving point impedance. Open circuit driving point impedance. Okay. Open circuit driving point impedance. driving point impedance. Okay. What is Y33? Anybody tell me? What is the Y33? Y33. Short circuit driving point admittance. See, one value you are doing with open circuit, other value you are doing with short circuit. So if you take inverse of one number, it cannot give the next number, right? Definitely, yes or no? Right? So it won't be equal to inverse of short circuit driving point admittance. Driving point admittance. Inverse of the short circuit driving point admittance. So open circuit driving point impedance will not be equals to inverse of the short circuit driving point admittance. But it is sure to say, listen please, but it is sure to say, inverse of the Y bus matrix will give Z bus matrix. Matrix inversion is okay. You take the whole Y bus matrix, take the inverse of that, it will give Z bus. That's okay. But you can't find out the individual element inverse to get the Z bus elements. It's a simple logic of matrix inversion, right? So I can say, but you know, always Z bus matrix is equals to inverse of the Y bus. Inverse of the Y bus, provided that the network remains same. Network elements remain same for the calculation of Y bus as well as for the calculation of Z bus. In bracket you write, provided that the network impedances remains same in both calculations. Same in both matrices calculations. Both matrices calculations. In both matrices calculation, we can say network keys remain same. Then you can say Z bus will be equals to the inverse of the Y bus. Then you might be getting a doubt that, sir, you said in this slide as a third conclusion, open circuit driving point impedance is not equals to inverse of the short circuit driving point admittance. But in the previous slide, you have written 1 by B, right? I have not changed the word. Kindly observe. Short circuit transfer impedance. What is the next one? Short circuit transfer admittance. I have not written open circuit. Okay, so both values we are calculating in the short circuit condition only. Inverse of one value will give the other value, obviously. But here, one value if with open circuit condition, other value with short circuit condition, you may not get inverse of one value as other value. Okay, so I think all of you understood this, what I said. Clear? Okay, now let's continue. I will ask one very simple question to you. Very simple question. Kindly observe. See, for example, I'll say like this. Y bus calculated to do load flow analysis. Okay, next one. Z bus calculated to do fault analysis. Y bus calculated for load flow analysis. Z bus calculated to do fault analysis. In that case, will the inverse of Y bus will give Z bus or not? Will the inverse of Y bus will give Z bus or not? Tell me please. Can I say this statement is going to be satisfied? Z bus is equal to Y bus inverse. Will it be satisfied or not? Inverse of one matrix is going to give other matrix. Yes or no? No, it won't give. The reason I will tell you. Particularly while you are constructing Y bus to do load flow, or if you are doing load flow analysis, Generator impedance, we should take steady state impedance. Generator impedance in the load flow, you should take steady state impedance. And if you are doing fault analysis, what is the generator impedance you should take? Subtransient impedance. In that case, in the Y bus what you calculated to do fault analysis will have the steady state impedance in that. Yes or no? Z bus what you calculated to do fault analysis will have subtransient impedance in that. Then definitely Y bus you calculated with steady state impedance, Z bus you calculated with subtransient impedance. One matrix inverse will not give the other matrix, right? Yeah. I don't know whether you are following this or not. Very simple thing. Very simple thing. This will not be equal. Okay. Please read that first statement we have written. Please read the first statement we have written. What is that? Z bus equals to Y bus inverse. Definitely Z bus equals to Y bus inverse. Provided that network will be remains same. If the network is different, how we can take up this statement? Very simple thing. We have calculated Y bus on one network, Z bus on a different network. And then how can I say one matrix inverse will give other one? If you keep network remains same and you take one matrix calculation, inverse of that will give the other matrix. Okay? Yeah, simple. Next thing. Let's continue with these are some conclusions. Go through them. Let's continue with construction of the Y bus matrix. Right? What are the various methods we have for the construction of Y bus matrix? That we'll be discussing further. Yeah. So let's take construction of Y bus matrix. Construction of Y bus matrix. First, let me think about methods to construct these Y bus matrix. Methods to construct these Y bus matrix. First method, direct inspection method, or you can say direct observation method. First method is direct inspection, or you can say direct observation method. Direct inspection, or you can say direct observation method. Second one we are going to name as singular transformation method. Singular transformation method. These are two methods to construct the Y bus. Most of the time our concentration will be on the first one only, direct inspection method, or you can say direct observation method. Let us take up the previous class discussion a little bit. Just look here. I've taken one example, right? This one. This is the example I have taken up. This is some example I have taken up. Just go through this example. Right. So it's an example network with certain bus voltages and all. Next, we have constructed the Y bus, right? Constructed the Y bus like this by using KCL equations at the nodes, right? We constructed the Y bus. Okay, kindly observe my words. See, already we have Y bus existing by the KCL equations. Just look here. This value we will call as capital Y11. This value we call as capital Y22. And this value we call as capital Y33. Observe the things quickly. Capital Y11, capital Y22, capital Y33. Y11, Y22, Y33. This value you call capital Y12, and this is capital Y13. And similarly, remaining things, if you want, you can write. Of course, you no need to write it. Just observe. Just observe the thing what I am saying. Look here. Standard node 1. Remove the current sources. Not required. Remove the current sources. Yes, I will ask one reverse question to you. Just listen to me. Very, very simple question. Of course, it's a reverse question to you. Look the thing. this current source I1 as 10 amperes. Keeping the current source as 10 amperes. Do you have any change in this matrix? Tell me please. I am keeping this current source as 10 amperes. Do we have any change in this Y bus matrix? No, we don't have any change, right? Okay, else. I am keeping one current source at bus 2 with 20 amperes extra now. At bus 2, I added one current source with a current of 20 amperes. Is there any change in these Y bus elements? Is there any change in the Y bus elements? No. See, my simple way of saying here is, whether you keep a current source or remove a current source in the original network, your Y bus elements will not be changed. Y bus elements depends upon only impedances or admittances of your network. Y bus elements depends upon only impedances or admittances of the network. Following all of you. That's why simply I will remove all the current sources existing in the network. I will be removing the current sources existing in the network, something like this. This current source I remove. This current source also I am removing. I1. Okay, listen. After removing these current sources, stand at node 1. Stand at the node number 1. What are the branches connected to node 1? What are the branches connected to node 1? Y10, Y12. Y10, Y12 admittances. Sum of these two values, Y10, Y12, is nothing but the value capital Y11. Nothing but the value capital Y11. Okay, next, you stand at node 2. What are the admittances of the branches connected to node 2? 3 branches are there. 1, Y12 number, next Y20, next Y23. Sum of these 3 admittances is a value capital Y2. Small y12 plus small y20 plus small y23. Summation is the value capital Y2. And if you stand at node 3, what are the branches connected to node 3? Y23, Y30. Sum of these two is a value capital Y3. Means just by looking at the network itself, are you capable to write the diagonal elements of the Y bus? Just by looking at the network itself, are you capable to write the diagonal elements of the Y bus? Yes or no? Yes. These are nothing but summation of all the admittances of the branches directly connected to the node. Summation of the primitive admittances of the branches directly connected to the node. Okay, next one. Look here. See, between bus 1 and bus 2, do you have any connection? Direct connection? Yes. Between bus 1 and bus 2, we have a direct connection. What is that admittance connected? Small y1. Negative of that value is a number capital Y1. Between bus 1 and bus 2, we have an admittance of small y12. Negative of that number is a value capital Y12, we can say. Okay, next 1, 2, 3, we don't have a direct connection. As we don't have a direct connection between 1 and 3, capital Y13 number will be 0. Capital Y13 number will be 0. Similarly, between bus 2 and bus 3, we have an admittance of small y23. Negative of that value is nothing but capital Y23. In the sense, off diagonal element, Y negative means it is coming negative, Harshvardhan. We constructed the Y bus, right? From that Y bus, we are comparing this Y bus with the network. That's it. That conclusion we are taking. Then we are thinking how to get the Y bus directly from the network given. First, we constructed the Y bus already. Now we are thinking about the method. That's the thing. Negative of this small y23 is appearing as capital Y23 number. Okay. So in that way, just by looking at the network itself, we are capable to construct the Y bus matrix. This method we are going to call as direct inspection method, or you can say direct observation method. Okay. Yeah. So I can say in the next slide, that method what we are taking on. Direct inspection method for the Y bus construction. Direct inspection method for the Y bus construction. So in this method, diagonal element of Y bus diagonal element of Y bus. It is nothing but sum of primitive admittances of the branches, primitive admittances of branches directly connected to the node. Directly connected to node. Sum of primitive admittances of the branches directly connected to the node. Okay, next one. Means I can say, for example, capital YII, if you want to know, diagonal element capital YII. Diagonal element capital YII. Nothing but summation of all admittances directly connected to the ith node. Directly connected to the ith node. Means I can say, maybe you have an admittance directly existing between ith node and 0, small yi0, small yi1, small yi2, and so on up to small yin. Whatever the primitive admittances we have connected to ith node, you sum up all these admittances, that is nothing but the value capital YII. Okay, next thing. Off diagonal elements of the Y bus. Off diagonal elements of Y bus. What do you mean by this off diagonal element? Just now we have discussed. No, it will be equal to negative value of primitive admittance of the branch directly connected between the nodes. Negative value of primitive admittance of the branch. Primitive admittance of branch directly connected between the nodes. Directly connected between the nodes. Off diagonal element, nothing but negative value of primitive admittance of the branch directly connected between the nodes. Yeah, let's continue. Means I can say capital YIK number is nothing but negative of primitive admittance between ith node and kth node. Primitive admittance between ith node and kth node. So you can call it is negative of small YIK. That you can say it as negative of small YIK. Capital YIK is equals to negative of small YIK. You can write negative of small YIK. Okay. See, for example, if you don't have any direct contact between the nodes, then that respective Y bus element, off diagonal element will come 0. Okay, right. For example, if there is no direct contact between ith node and kth node, then obviously small YIK number is 0. Capital YIK also comes to be 0. Capital YIK number also comes to be 0. Small YIK number is 0. So automatically capital YIK also comes to be 0. Okay, so as a practice, I will be taking up one problem here, and I will be constructing Y bus network for that problem, and then we will take up some more conclusions with respect to the Y bus matrix further. Okay, yeah. So I'm moving to the next slide to take up one problem. Kindly go through it. construct the bus admittance matrix for the following single line diagram where all the impedances are given in per unit form. But you people will ask me, sir, can we get this type of question in the exam? Can we get this type of big question in the exam? You don't get it. You don't get it in the exam, this type of question. But why I am discussing this question is just to take up some more conclusions regarding the Y-bus matrix. For that purpose only, I am going to solve this question. Yeah, let's continue. Look here. We have a 5-bus system here. Just identify the buses here. This is a bus 1. Bus 1 and it's a bus 2. Okay, and it's bus 3 and 4, 5. Like this, we have 5 buses. 5 buses. Now, you convert this given single line diagram into its per phase mode. Convert this given single line diagram into its per phase mode. Per phase model, right? 1, 2, 3, 4, 5 buses. Convert this into per phase model, and then you take up only impedances. Remove the current sources. Take up only impedances and try to construct the Y-bus. Yeah, let's move ahead. Directly, I am saying per phase network. Per phase network. Okay. Observe. This is a bus 1 first. What do you have at bus 1? You have a generator. Remove the current source. Take up only impedance of the generator. J0 point. It's a 0 reference. Neutral, you can say. 0 reference node. It is an impedance ZG. Next, bus 1 to bus 2, we have a transformer represented as a series impedance in per unit domain. ZT. You call it ZT1 better. ZT1. Next one. Bus 2 to bus 3, you have a line. Bus 2 to bus 3, we have a line. Like this, you call this as ZL1. Line impedance as ZL1. Bus 2 to bus 4, you have one more line. You call it as ZL. Bus 2 to bus 4, you have one more line. You call this as ZL. Like ZL. Next, bus 4 to bus 5, you have a transformer J0 point. Bus 4 to bus 5, you have a transformer ZT2. Next one, bus 5, you have a generator. You keep only impedance of the generator, remove the current source, that is ZG2. This is a reference node. ZG1, ZG2. ZG1, ZG2. Right. Next, immediately what I'll do is, I'll try to convert all these impedances into form of admittances. Let's write impedance values first. It is J0.2 and you'll have J0.3, this number. This is J0.2 again. I think line 2 J0.1 and this transformer 2 is J0.2. Generator 2 value was J0. Like this we have impedances. Next, in the very next step, I will take admittance network, primitive admittance network by converting all these impedances into the form of admittances. Primitive admittance network. Admittance network. We copy the same diagram as it is. In the same diagram. Yeah. Let's see this. So I will be converting these things into admittance form. YG1 first. YG1 admittance of the generator. 1 by J0.2. This will come to be minus J5. Minus J5. And YT1 1 by J0.3. YT1 is 1 by J0.3. This number is minus J3.333. Next, YL1 1 by J0.2, that will be minus J5. YL1, 1 by J0.2. So it will be minus J5. Next, YL2, 1 by J0.1. That will be minus J10. 1 by J0.1. So it will be minus J10. Next, YT2, 1 by J0.2. YT2, 1 by J0.2. This number will be minus J5. Next, YG2, 1 by J0.3. That will be minus J3.333. 1 by J0.3, it will come as minus J3.333. So like this, you will get these primitive admittance networks, primitive admittance. Why you are bothering about ground, whether the neutral is grounded or ungrounded? We are drawing only positive sequence network. We are drawing only positive sequence network. Why you are bothering about groundings and all? And if you are getting that type of question, why don't you ask about transformer? Why don't you ask me about transformer? Transformer means you can represent a series impedance. Right. Let's continue. So first, let's identify these bus numbers in a proper way. Bus 1, bus 2, bus 3, 4, 5. Clear. What's the size of Y bus to be expected? What is the size of Y bus to be expected now? 5 by 5. Size of the Y bus will be 5 by 5 meters. Good. And if you calculate capital Y11 number, capital Y11, that is nothing but summation of all admittances directly connected to bus 1. What are the admittances directly connected to bus 1? YG1, YT1. This summation is a value capital Y11. Let me write the whole matrix in a single step. Y bus matrix. Right? So these are bus numbers I am saying you. Bus 1, bus 2, bus 3, bus 4, bus 5. Okay, similarly, you can write here bus 1, bus 2, 3, 4, 5. Okay. Capital Y11 is nothing but sum of admittances connected to bus 1. Means it is YG1 plus YT1, you should say. This number is YG1 plus YT1. Let me write diagonal elements first. Let me write these diagonal elements first. After that, we will think about the half diagonals. Next, capital Y22. Capital Y22. How many admittances directly connected to bus 2? 3 admittances. YT1, YL1, YL2. Okay. So YT1 plus YL1 plus YL2. YT1 plus YL1 plus YL2. Next, bus 3. Bus 3. What are the admittances connected to bus 3? Only YL1. Only YL1 should take at the location of 3, 3. Next, 4, 4. 4, 4 return. 4, 4. Bus 4. 2 admittances are directly connected. One is YL2, next one is YT2. So YL2 plus YT2, we should say. YL2 plus YT2, we should say. At bus 5. At bus 5. 2 admittances directly connected. One is Y22, next one is YG2. T2, G2. YT2 plus YG2. That's it. So this is a way of taking up the diagonal elements. Diagonal elements. Clear. I'll write the numbers in the very next slide. Let me fill this one. Let me fill this one. What is capital Y12? What's the value capital Y12 in the Y bus? Negative of primitive admittance of the branch directly connected between bus 1 and bus 2. Between bus 1 and bus 2, we have a direct contact. That value was YT1. Negative of that number, you have to substitute here. So it is minus YT1. Minus YT1. YT1. Next, 1, 2, 3. 1, 2, 3. No direct contact between bus 1 and bus 3. So it will be 0. 1, 2, 4. Do you have any direct contact? No. No direct contact between bus 1 and bus 4. 1, 2, 5. No direct contact. So obviously, Y14, Y15 numbers will be 0. And whatever the row you got here, same thing you can repeat as a column. Because you know, Y bus is a symmetric matrix. Else, if you want, you do this calculation. What is capital Y21? What is capital Y21? Negative of the primitive admittance connected between bus 2 and bus 1. What is the bus 2 to bus 1 admittance? YT1 value. Negative of that will occupy this place. That's it. Simple. 3 to 1, no direct contact, 0. 4 to 1, no direct contact. 5 to 1, no direct contact. Like that you can fill if you want. Okay, next. What is capital Y23 number? Capital Y23. 2 to 3, do you have any direct contact? Yes. YL1 is a direct contact. Negative of that admittance will occupy this place. Negative of YL1 will occupy that place. Okay, next one. Capital Y24, 2 to 4, do you have any contact? Yes, capital Y24 is there. Negative of YL2. Negative of YL2. 2 to 5, do you have anything? No, so it will be 0. 2 to 5 will be 0. So you can copy that row down to this column in this manner. Next one, 3 to 4, observe 3 to 4. No contact between 3 and 4, direct contact is not there. Between 3 and 4, 0. 3 to 5, any direct contact between 3 and 5? No direct contact between third bus and fifth bus, 0. So you can repeat that. And you can say 4 to 5 here. 4 to 5, direct contact is there, minus YT2, and the same number will be repeated at this place. This is a Y-bus matrix in terms of the primitive admittances. You join ground point together, you do your own calculation if you want, mister. You join these ground points. What's the issue in that now? Ground point you can join, or neutral point you can join. That's the reference. That's the reference operating at 0 potential. Then can you add this YG2 and YG1 together? Can we add these two? Then add all the things. You will get only one node, right? Okay. Continue with this one. Keep these elements quickly. Numbers we have to take up. Y-bus numbers. Bus 1, bus 2, 4, 5. Okay. So similarly here, 1, 2, 3, 4, 5. Simple, very simple observation. Capital Y11, you take YG1 plus Y means it is minus J 8.333. Write the numbers quickly if you have. Minus J 8.333. Capital Y12 is plus J 3.333. Y13 is not there. Y14, Y15 also not there. So it is J 3.333 and 0, 0, 0. Okay. Capital Y22, if you think it is minus J 18.333. Minus J 18.333. And 2, 3. 2 to 3, it is a plus J5 you are going to get. And then 2 to 4, you have plus J10. J10 you will get. And 2 to 5, no direct connection, so it will be 0. You repeat that here. It is J5, J10, 0. And capital Y33, if you call 33, it is plus J5. Plus J5. And 3 to 4, no direct connection. 3 to 5 also no direct connection. So you can keep zeros here. It's minus J5. 3 minus J5. 0, 0. And 4, 4. 4, 4, if you think it will be minus J15. 4, 4 minus J15. And then 4, 5. 4, 5 plus J5. And here it's again plus J5, negative of that number. And 4, 5, 5. 5, 5 means YT2 plus YG2. It will be minus J 8.333. Minus J 8.333. Observe. Is it clear? Yeah. All of you getting this matrix? Y-bus matrix. So the conclusions what we are going to take up further. J55 is minus J10. Let me check once. Sorry, it is minus J. Minus J. I think it's okay. Now? Yeah, good. Minus J 8.53. Yeah. So let me bifurcate the diagonal elements and off diagonal elements first. These are the diagonal elements we have. Diagonal elements. And this is a upper half diagonal and that's a lower half diagonal. Let me identify that also. It is a upper half diagonal. Upper half diagonal. And this is a lower half diagonal, you can say. Lower half diagonal. Upper half diagonal, lower half diagonal, and this is a diagonal. This is diagonal. Next. Next thing. First, one very simple conclusion from this Y-bus matrix. Very simple conclusion. See, some of the elements in the half diagonal are zeros. Maybe Y13 is 0, Y14 0, Y150, Y250, like that we have. Some elements are 0 in the half diagonals, upper as well as lower. But in the diagonal, no element is 0. Means definitely for a practical power system network I am talking. Not with respect to any network what you construct. With respect to practical power system network, always the Y-bus matrix will have non-zero diagonal elements. Non-zero diagonal elements, right? So I'll say the first conclusion here. First conclusion for a practical power system network. Practical power system network. The diagonal elements in the Y-bus, diagonals in the Y-bus will be always non-zero numbers. Always non-zero numbers. It's the first conclusion we can see. First conclusion is for a practical power system network, the diagonals in the Y-bus will be always non-zero. Half diagonal elements, some elements may be 0, some elements may not be 0. That's okay. That's okay. We will make that comment also. We'll make that comment also. Just listen to me. Listen to me. Asking a reverse question. First, we have taken one network, constructed the Y-bus. We got the Y-bus. For example, by looking at this Y-bus, all of you, please tell me. By looking at this Y-bus, I am observing that this number Y35 is 0. In this Y-bus, I am observing that Y35 value 0. What is the meaning of that? Tell me, please. Y35 number is 0. What is the meaning of that? There is no direct connection between buses 3 and 5. No direct connection between buses 3 and 5. Okay. Next. I am observing that Y14 number 0. Y14 number 0. What is the meaning of that again? No direct connection between bus 1 and bus 4. No direct connection between bus number 1 and bus number 4. Okay. For example, if you see this number, what we call Y24, you are getting this number J10. Y24 number is J10. What is the meaning of this one? We have a direct connection between bus 2 and bus 4 with some admittance value, which is nothing but negative of this number, means minus J10. Minus J10 admittance exists between bus 2 and bus 4, you can see. All of you getting these words? Now, my question is, just by looking at the Y-bus itself, are you capable to tell which buses are directly connected by the branches? Are you capable to tell which buses are directly connected by the branches? Yes or no? Yes. So that we can say Y bus matrix is going to represent the connectivity between the buses. Y bus matrix represents the direct connectivity between the branches. Okay. Yeah. So that statement I'm writing now. That statement I'm writing. Y bus gives the information about direct connectivity between buses, or you can say nodes. Direct connectivity between buses, or you can say nodes. Okay. Next thing. One more simple thing. Look here now. Let me copy that matrix to this next slide, because you feel it's a cumbersome. Look in this matrix now. Same matrix only. Same matrix I have copied here. What is summation of first row? Tell me quickly. Summation of first row. Summation of second row. Third row. Fourth row. Fifth row. Tell me sum of the elements in the row. First row summation. First row summation is minus J5. Second row 0. Third row 0. Fourth row 0. Fifth row it's minus J3. Sorry. Minus. This will be minus J 3.33. Minus J 3.33. All of you getting this? All of you getting this one? Minus J5, 0, 0, minus J 3.33. Can you please tell me, if you are summing up the first row, I'm getting some number as minus J5. What is it minus J5? What is it minus J5? Just observe in the network what you can say. What is it minus J5? That is nothing but admittance of the branch connected between bus 1 and reference. Nothing but the admittance of the branch connected between bus 1 and reference. See, if any element, impedance, admittance, whatever it is, if any element connected between a particular bus and reference, what we name it generally? Shunt element. We name that as shunt element in the system. Means simply, if you take up summation of a complete row of a Y bus, it will give you admittance of the shunt element connected at that respective bus. Getting this? Yeah, I'll check the second row, Harshvardhan. It's plus J10 only, Harshvardhan. Second row, it will be plus J10 only. Negative of admittance of branch between 2 and 4. 2 and 4, you have minus J10 already. Negative of that means plus J10. Yeah, all of you getting this? Please tell me. I will write that statement. As a third conclusion, of course. Third conclusion. Some of the elements in a row of Y bus, in a row of Y bus will give admittance of shunt element. Connected at that bus number. And 2 and 4 are at the row numbered bus, exactly speaking, at the row numbered bus, at that row numbered bus. I'll try to write in an elaborate way in the form of equation. Yeah, please complete it and I will write this one. Please complete it. Yeah, fine. So I can say shunt element at the ith bus, or if you take ith row summation, ith row summation in the y bus actually, ith row summation in the y bus, capital yi1 plus capital yi2 plus capital yi3 plus and so on, capital yii plus and so on, capital yin. If you take up that summation of that ith row entirely, you take up the summation of the ith row entirely, it will give small yi0. Small yi0 is nothing but shunt element connected at the ith bus. Shunt element connected at the ith bus. Yeah, let me check back that node 2, many of you are complaining about node 2. What happened to node 2? Is 0. What's there in that? Node 2, do you have any shunt element? At node 2, do you have any shunt element? Any element is connected between node 2 and reference? Any element is connected between node 2 and reference? No. Then you don't have any shunt element at node 2. What the doubt you have further regarding node 2? Node 2. Yeah. So the small yi0 is nothing but shunt admittance at ith node. Shunt admittance at ith node. Shunt admittance at the ith node. Clear? Next thing. Let me move ahead. Next, one more conclusion here. One more conclusion. Yeah, can I say the statement? You have to tell, is it true or not? Is it true or not? If you have any generator at a bus, look. If you have a generator at a bus, the generator admittance what you have, will act as shunt element. Generator admittance, whatever you have in the network, is going to act as shunt element in the Y bus and Z bus constructions. In the construction of the Y bus and Z bus, definitely. Right? So that statement, that conclusion also I'll take. That's the fourth conclusion. Generator admittance or impedance will act as shunt element in the network. Shunt element in the network will act as shunt element in the network. Okay, next statement. Just from the Y bus only we have to observe now. Y bus. Observe here. Just have a look at these off diagonal elements. Off diagonal, upper half diagonal, lower half diagonal. Upper half diagonal, lower half diagonal. Let's say upper half diagonal. Concentrate on the upper half diagonal. How many non-zeros you have here? In the upper half diagonal, just count it. How many non-zero numbers? How many non-zero numbers here? In the upper half diagonal, how many non-zero numbers here? 1, 2, 3, 4. 4 non-zeros in the upper half diagonal. Simple thing. Just I am asking you to count. 4. Okay, good. 4 non-zeros we have in the upper half diagonal. Means I can say between buses, can I say we have 4 interconnections? Between buses, we have 4 interconnections. Means I can say bus 1 to bus 2, we have 1 connection. Bus 2 to bus 3, we have 1 connection. Bus 2 to bus 4, 1 connection. 3 to 5, 1 connection. Total number of interconnections in the system are only 4 interconnections, we can say. Following all of you. If you want, you look back to the original network, what you have. Look back to the original network. Just look this network, better. Problem. This network. Between bus 1 and bus 2, we have 1 connection. Bus 2 to bus 3, second connection. Bus 2 to bus 4, third connection. Bus 4 to bus 5, fourth connection. Total, how many interconnections we have between the buses now? 4 interconnections we have between the buses. So we have 4 non-zero numbers in the upper half diagonal, 4 non-zero numbers in the lower half diagonal. So simply number of non-zero numbers or number of non-zero elements in the upper half diagonal equal to number of interconnections between the buses. Similarly, lower also. Okay. So I am writing the statement. Sir, in Y bus, if 2, 1 not connected, or it will be open or short, then the value is 0. Then in the diagonal, Y bus will be 0. Yeah, we'll discuss about it, Yogeshri. Let me write that comment. So I'm showing here. That's fifth comment I have to make. Fifth conclusion, you can say. Number of non-zero elements in upper of diagonal is equal to number of non-zero elements in lower half diagonal, non-zero elements in lower half diagonal. These two are equal, is equal to number of interconnections between the buses. Number of interconnections between the buses. Interconnections between buses. What do you mean by number of interconnections between the buses here? What do you mean by number of interconnections between the buses? That is nothing but number of generators, number of transformers plus number of lines. That's it. Transformer will act as an interconnection. Line will act as an interconnection. Generator will act as a shunt element in the network. Yes. So this is nothing but number of transformers plus number of transmission lines. Number of transformers plus number of transmission lines. Okay. So I'm showing 32 here. Please write if you are still doing it. Please kindly complete the 32 slide number 32. Okay. Yeah. So let me take up all these conclusions to take up the extension for this one. Extension for this. Let's take some example here. I'm taking some example. So let's say we have 100 bus power system network. 100 bus power system network. Okay. So in that 100 bus power system network, we have 20 generators. 20 number of generators here. And then we have, let us say, 40 number of transformers, or 45, say. 60 number of transformers we have. 60 number of transformers we have. And then we have, let us say, 120 transmission lines. 120 number of transmission lines we have. Total number of buses 100 buses. 20 generators we have in the system. 60 transformers we have in the system. 120 transmission lines we have in the system. First of all, you tell me, what is the size of the Y bus matrix here? What is the size of the Y bus matrix? Anybody? Tell me please. 100 by 100. Number of buses by number of buses will be the size of Y bus matrix. So Y bus matrix size will be 100 by 100. How many total number of elements you have in the Y bus now? How many total number of elements you have in the Y bus? 100 into 100, na? It will be 10,000 elements you have in the Y bus. 10,000 elements you have in the Y bus. Let me write it. Total number of elements in Y bus. Total number of elements in the Y bus matrix, 100 into 100, it will come like 10,000. Come like 10,000 elements you have in the Y bus. Okay, next thing. Simple, very simple. Don't confuse. Whatever the conclusions we have taken earlier, that I am going to adapt to this problem. See, we have one diagonal, right? We have a diagonal. How many elements you have in the diagonal? How many elements you get in the diagonal? 100. 100 diagonals you have. 100 diagonals. Okay, remaining how many? 10,000 minus 100. 10,000 minus 100 means 9,900. 10,000 minus 100 means 9,900. Half 9,900 by 2 in the upper. Remaining half 9,900 by 2 in the lower. 9,900 by 2 upper. 9,900 by 2 lower. In the upper half diagonal, we have 9,900 by 2. In the lower half diagonal, we have 9,900 by 2 elements. We have elements. Okay, done. Next thing. Very simple. Just observe. Here. Simple question only. Diagonals we have 100. Diagonals we have 100. Can you say all these diagonals will be non-zero? 100 diagonals we have. Can we say all these 100 diagonal elements will be non-zero in a practical system? Definitely. Yes. So I can say in this 100 diagonal, simply I can write 100 non-zeros. Red color I am writing non-zero elements. 100 non-zeros. You see, half diagonal 4,950 elements here in the upper half diagonal. How many elements will be non-zero here? In the upper half diagonal, how many elements will be non-zero? Tell me please. That is nothing but number of interconnections, right? How many number of interconnections you have in the system? Number of interconnections in the system will be number of transformers plus number of lines. It will be 180 non-zeros. In the upper half diagonal, we have 180, not 200. Not 200. How you count the generator here? Sajjan Singh. How you count the generator? Generator should not be counted. Good. Okay. So, number of non-zeros in the upper half diagonal will be 180. Obviously, in the lower half diagonal also, number of non-zeros will be 180. 180 non-zeros in the upper half diagonal, 180 non-zeros in the lower half diagonal. I think all of you getting this point? Now, the simple question is, total number of non-zeros are how many? Total number of non-zeros will be 180 plus 180 plus 100. It will come to be 460 elements as non-zero numbers in the whole Y bus matrix. Okay? Yeah, let me write here. Number of non-zeros. Number of non-zero elements in Y bus, nothing but 100 diagonal, 180 upper half diagonal, 180 lower half diagonal. It will come to be 460. It will come to be 460 elements. Yeah, next I can say non-zeros are 460. Then how many zeros here? Number of zero elements in the Y bus. Number of zero elements in the Y bus. How many you have? 10,000 total minus 460. Total 10,000 minus 460. It will be 9,540. 9,540. That will be number of zero elements. Number of zero elements will be 9,540. Tell me, listen. It's a very simple one to understand now. Total number of elements 10,000. Total number of elements 10,000. In the 10,000 elements, 9,540 zeros. So major portion of matrix looks to be zeros only. Major portion of this matrix looks to be zeros. This type of matrix we are going to call as sparse matrix. Sparse matrix in the sense it is a matrix consisting a large number of zero elements, right? So I can say now, as majority elements are zeros, Y bus is a sparse matrix. Y bus is a sparse matrix. As majority elements are zeros, Y bus is a sparse matrix. And the percentage sparsity is nothing but number of zeros by total number of elements in the Y bus. Okay, so I can write percentage sparsity is equal to number of zeros in the matrix by total number of elements in the matrix. Total number of elements in the matrix. This we should multiply with 100%. That we should multiply with 100%. What are the total number of zeros we have? 9540. And total number of elements, 10,000. So it will come to be 95.4%. 95.4%. So percentage sparsity in the sense, how many? That's what I explained till now. What the sparse means, again you are asking. What is it? If the network or if the matrix is consisting many elements as zero, that we can say as sparse. If you want English meaning, just type in Google, you will get it. If you want English meaning, sparse. Okay. So percentage sparsity. So 95.4% sparse. In the sense, 95.4% of whole Y bus elements will be zero. Remaining how many? 4.6% will be non-zeros, right? That implies you can say 95.4% elements are zero, or you can say remaining how much? 4.6% elements will be non-zero. Elements will be non-zero. 4.6% elements will be non-zero. Yeah. Clear? If the matrix is this much sparse, storage of this matrix will be easy. Y bus storage will be easy. Okay. Means in the computer, if you want to store, you don't need to store zero. You have to store only non-zero elements. Yeah. Let's think in this manner. In the next slide, I am taking up. Okay, Y bus is a sparse matrix. Is okay. Y bus is a sparse matrix. What about Z bus matrix? What is Z bus matrix? Z bus, is it a sparse or non-sparse matrix? Z bus. It will be a non-sparse matrix. Z bus is a non-sparse matrix. Else you can say Z bus is a full matrix. I will explain you how it is. First, let me write these things. Y bus for a big power system network or for a practical power system network is a sparse matrix. Sparse matrix. Whereas Z bus is a full matrix. Z bus is a full matrix. Right here for practical power system network means big power system. For a practical power system network means for a big power system network. Yeah. So let's take one network here, maybe with some number of buses. 9 buses I am considering. In the next slide I have to show. Next slide. I have a 9 bus system. I'll show that system here. Kindly observe. You no need to draw, just observe. Bus 1, bus 2, bus 3, bus 4, 5. Right. So at bus 5, let me show one generator. Okay, one more generator at bus 5. Next it's a bus number 6. I am saying one more generator I will show. And we have bus number 7. Let's say 7 buses. We'll add one more. So 8 bus. Like this, we have 8 bus system. 8 bus power system network, something like this. These are the buses. Let me highlight. Buses 1, 2, 3, 4, 5, 6, 7, and this is 8. Something like this. 8 buses. 8 buses. And you know already if you have a generator that we will be representing simply as a impedance by removing the current source. And all these lines are lines only. So these lines also represented as series impedances. So let me keep this generator as a simple impedance with reference node. And this one again with an impedance and with a reference node. And here then we'll keep some impedance with some reference. Okay, please tell me how many number of nodes we have in the system? Please tell me how many number of nodes we have in the system? Including the reference, you say 9. Including the reference, you say 9. But excluding reference, we should take as 8 only. So if anybody asks you simply how many nodes we have in the system, you answer it as 8. You answer the total number of nodes as 8, excluding the reference. Okay, and your size of Y bus will be 8 by 8 matrix. Z bus size is also 8 by 8 matrix. Y bus is 8 by 8. Z bus is also 8 by 8 matrix. Okay, let's continue. Let's continue here. Simple question I will ask you. Very simple question. What will be the value Y18? How much? Capital Y18. Anybody? Capital Y18. 0 or non-zero? 0. No direct contact. No direct contact between buses 1 and 8. So capital Y18 number is 0. Okay. What is Z18? Anybody tell me? How to calculate Z18 in the network analysis method? Listen. In the network analysis method, how to calculate Z18? We should take V1 by I8. We should take this ratio, voltage at bus 1 to the 8th bus current injection I8. V1 by I8. Just look this one. See, for the calculation of that Z18, you have to keep one current source at the 8th bus. You should keep some current source at the bus number 8. Listen here. After giving that current injection at 8th bus, current will flow in the circuit. What will be the value of V1? Is it 0 or non-zero? By injecting some current at the bus number 8, current will enter into that line and flows in the network. What will be the voltage at the bus 1? Anybody? That will be definitely non-zero. Bus 1 voltage will be definitely non-zero. Definitely some voltage will exist because you have a source in the network. So if you take up that V1 by I8 number, this number will be definitely non-zero value. Definitely it will be non-zero. All of you getting my words? All of you getting this calculation? Next one. What is the value Y38? How much? 3 to 8. You have a contact. You leave it. You will get a confusion. Take Y48. How much? Y48? 48. Any direct connection between bus number 4 and bus number 8? Any direct connection between bus number 4 and bus number 8? No direct connection. So if we don't have any direct connection, definitely Y48 will be 0. Y48 will be 0. Then what is the value Z48? Anybody? V4 by I8. V4 by I8. Is it 0 or non-zero? V4 by I8. See, by keeping this current at the 8th bus, definitely bus number 4 will experience some non-zero voltage. Bus number 4 will experience some non-zero voltage. Because of that, definitely you can say this Z1, Z48 number also non-zero. See, not only that, very simple technique. Y bus elements we have clarity, and we know Y bus is a sparse matrix. Y bus elements we have clarity already. Y bus is a sparse matrix. See, while you are calculating Z bus, we have to go with the current injection technique. inject some current at certain bus. Inject some current at certain bus. By injecting that current, can you get voltages at all the buses in the system? Can you get voltages at all the buses in the system? Yes or no? Yes, definitely V1 will be non-zero, V4 will be non-zero, V2 non-zero, V3 non-zero number, and then V5 non-zero number, and then V6 non-zero, V7 non-zero, V8. All the numbers, all the voltage will exist, right? So that voltage to current ratio will give the Z bus elements maybe a particular column. Whole column or whole row in the Z bus will be non-zero. So in that sense, if you are calculating Z bus elements of this network, definitely all the elements in the Z bus matrix will come as non-zero numbers only. By that way, we can say Z bus is a full matrix. Z bus is a full matrix. All of you getting my words? Is this clear? Right? So that's what the conclusion we said just now. Z bus is a full matrix. So Z bus will not represent any connectivity between the buses. Because all the elements are non-zero means you can't say which buses are directly connected and which buses are not directly connected. So Z bus will not give any information about the connectivity between the nodes, but Y bus will give the information, right? So if you want, I will write that statement also. As Z bus is a full matrix, it won't give information about, direct connectivity between the buses. Direct connectivity between buses or between the nodes. Direct connectivity between the buses, or you can say between the nodes. Yeah. So have a break for 20 minutes. After break, 20 minutes break. So after break, we'll be continuing with some problems on Y bus. Okay. So I have resumed audio, video, and screen. Okay. So let's take up the first question in this matrices. Some questions with respect to sparsity here. We'll see some problems with respect to sparsity. After that, we'll move on to so look at this question. A 150 bus power system network has a Y bus matrix with 96% sparsity. 96% sparsity. The number of interconnections will be how many? Number of interconnections will be how many? Simple. You see, first of all, if you have 150 bus power system network, size of Y bus will be 150 by 150. Size of Y bus will be 150 by 150. Then what will be the total number of elements in the Y bus? 150 into 150, na? So you get 22,500 elements. Okay. Total number of elements. Total number of elements in the Y bus. Nothing but 150 into 150. So that will be 22,500. 22,500. Okay. See, this matrix is 96% sparse. 96% sparse in the sense 96% of 22,500 elements are zeros. Means obviously remaining 4% will be non-zero, we can say. So I'll write number of zero elements will be 96% of 22,500. 96% of 22,500. Okay, now number of non-zeros. Number of non-zeros will be 4%. Means 0.04 into 22,500. 0.04 into 22,500. How much is this number? You tell me. Number of non-zeros. Anybody? How many number of non-zeros we have? 900 non-zeros. 900 non-zeros we have. Now, if you look at that 150 by 150 Y bus matrix, 150 by 150 Y bus matrix, just observe. So in this matrix, diagonals will have 150, na? Diagonals will have 150. That will be definitely non-zero numbers. Diagonals what we have here, 150. This 150 will be non-zero. 150 non-zeros we have in the diagonal. Remaining how many? Remaining will be 900 minus 150. Remaining will be 900 minus 150. That will be coming like 750. 750. In that 750, half in the upper half diagonal, half lower half diagonal. So 750 by 2 non-zeros in the upper, 750 by 2 non-zeros in the lower. 750 by 2 non-zeros in the upper, 750 by 2 non-zeros in the lower. Means you get 375 non-zeros in the upper. What do you mean by number of interconnections? That is nothing but number of non-zeros in the upper half diagonal or number of non-zeros in the lower half diagonal. It will be the number 375. That's it. Okay. So number of interconnections in the system, number of interconnections between the buses, interconnections between buses equal to 375. 375 we can say. Okay. If you want to write number of non-zeros in the upper half diagonal here, number of non-zeros in upper half diagonal, So this number is nothing but 375. 375. Simple question. So let's take up one more question. With respect to sparsity only, I am taking up this. So observe this question. Go through this once. See this. Yeah, I'm really sorry, network issue. Say this. A power system network consisting of 430 interconnections between the buses. And Y bus of the network is 98.09% sparse. The approximate number of buses in the system are how many? Look here. Number of interconnections are 430. Let me write it. Number of interconnections are 430. 430. So it is 98.09% sparse. What is the meaning of that? Y bus is 98.09% sparse. That implies 1.91% elements are non-zero. Okay. 1.91% of elements are non-zero. Okay. For example, if you assume that number of buses are n, that's what we have to calculate in this problem. What will be the total number of buses now? So total number of elements now. If number of buses are n, what will be total number of elements in the Y bus? N square. So 1.91% of n square will be non-zero. Yeah, let me write. So I'll say now, let n will be number of buses. So I can write number of non-zeros will be equal to 1.91% of n square. 1.91% of n square means it is 0.0191 n square. 0.0191 n square. Yeah, good. But you know, number of non-zeros in the matrix. If you think, if you take up the Y bus simply like this, it's a n by n matrix, you can say. N by n matrix. In that, n elements will be in the half diagonal, which are non-zeros. N elements will be in the half diagonal, which are non-zeros. Okay. Next, 430 interconnections, he said, na. So 430 non-zeros in the upper, 430 non-zeros in the lower. 430 non-zeros in the upper, 430 non-zeros in lower. Then what will be the total number of non-zeros now? 430 plus 430 plus n. 430 plus 430 plus n. So I'll write here itself. N plus 430 plus 430. So 860. Take to the other side. Then you can write 0.0191 n square minus n minus 860 is equals to 0. 0.0191 n square minus n minus 860 is equal to 0. This we have to solve. This equation we have to solve by means of quadratic expression, right? So you can write n is equals to minus b means plus 1 plus or minus square root of b square minus 4ac. 4ac by 2a. 2 into 0.0191. Okay. So you write this one, you rewrite this one. You will get two answers now. Two answers. We have to take appropriate option among the two. Let's say first one. If you take minus symbol, square root of, you find out the square root number. Find out this number inside the square root. How much? Number inside the square root. 1 plus 0.0191 into 4 into 860. It is 66.704. This number is 66.704. Denominator we have 2 into 0.0191. It will be 0.0382. Is one option. Other option will be n is equals to 1 plus square root 66.704 by 0.38. Okay, calculate this number how much? Tell me. So first number will come first number 1 minus square root of 66.704 by 0.38. So this number is minus 18.6762. So it's not a proper option to be chosen because number of buses, it's a positive number. Na? Number of buses, it will be a positive number. So it's not a proper option. And what is the another value? Another value. So you'll have 1 plus square root of, it is 66.704, okay, by 0.382. So it will be, it is 0.038, right? I'm really sorry. It is 0.038. 0.0382. So it will be 187.62. Negative number anyhow. It's not a correct one. And it is, if you calculate this, you are getting this like 239.98, and you write this close to 240 buses. 240 buses. Fine. So 240 is the answer to be selected. 240 is the answer to be selected. 240. Simple question. So let's take one more. Let's take one more question. In that sparsity technique only. Yeah, go through this. A power system network has the Y-bus matrix with the total number of elements as 16,900. 16,900, in which 16,410 zeros. 16,410 zeros. The system has 30 transformers. The expected number of transmission lines are how many? How many number of transmission lines we can expect? What are the total number of elements in the Y-bus? 16,900, right? Total number of elements are 16,900. Means how many buses you can experience now? How many buses you can expect in the system? How many buses? Generally, total number of elements will be n by n, right? N square. So you can say number of buses n. So n square equals to 16,900 in the sense. Number of buses will be 130. So we have 130 buses in the system. 130 buses in the system. Okay, now in that matrix of 130 by 130 now, in the matrix of 130 by 130, 16,410 zeros. 16,410 values zeros. How many non-zeros you have? 590. 590. In that 590 non-zeros, sorry, 490. 490. In that 490 non-zeros, 130 in the diagonal. So 490 minus 130 in the sense it will be 360. Half in upper, half in lower. 180 in the upper. So 180 number of interconnections. Transformers 30. Right. If you deduct 30, it will be 150. Number of expected transmission lines will be 150, we have to say. Clear? Yeah, let me write in a detailed way. Just look here. Y-bus matrix I am showing 130 by 130 size. 130 size. Okay. So diagonals we have 130 non-zeros. Diagonals we have 130 non-zeros. Let me write first. Total number of non-zeros here. Total number of non-zeros equal to total number of elements 16,900. From this you should subtract 16,410. So it will be 490. In that 490, 130 is in the diagonal. Remain 360. So 360 by 2 upper, 360 by 2 lower. You write now. Number of non-zeros in the upper half diagonal. Number of non-zeros in the upper half diagonal. Upper half diagonal is equal to 360 by 2. It will be 180. 180. And you see number of non-zeros in the upper half diagonal means it will be number of transformers plus number of lines. Number of transformers plus you write number of lines. And that will be nothing but 180. You know, transformers will be 30 in the data given, 30 transformers. So therefore, number of lines equal to number of transmission lines will be nothing but 180 minus number of transformers. This number will come as 150. So total number of transmission lines in the system are 150. So we have to fill that blank with 150 number. 150. All of you getting this? All of you getting this one? Clear? Yeah. So let's move. Let's move. So now we will be taking up some problems with respect to Y-bus. Till now we discussed some problems on sparsity. Now we are going to take up some problems regarding the Y-bus matrix construction and all. Yeah. So let's say first problem here. First problem. Go through it. Is from that additional questions file. From the additional questions file. Look here. Consider the following bus admittance matrix of a 4-bus power system. Bus admittance matrix of a 4-bus power system. Find at which buses shunt reactive and shunt capacitive elements exist. At what buses we have shunt reactive element, so-called shunt inductors. At what buses we have shunt capacitive elements, means shunt capacitors. Okay, that we have to do. Clear? Simple. How to know whether we have a shunt capacitor or shunt reactor at a given bus? How to know whether we have a shunt capacitor or shunt reactor at a given bus? Tell me please. Just we have to sum up the row and we have to check whether that number is 0 or non-zero. Based on that, we should decide whether we have a shunt element or not at that bus. And based on the J symbol, plus J or minus J, we should decide is it a reactive or inductive in nature, sorry, capacitive in nature, right? So I'm taking up that Y bus given for this 4-bus system. This is a Y bus given for a 4-bus system. Now, what is this first row summation? What is the summation of the first row? That will give small y10, na? First row summation will give you small y10. How much is that? Minus J3. Minus J30 plus J10 plus J17, it will be minus J3. What is the summation of second row? What will be the summation of the second row? Means y20. How much is that? Take up this one, J27 minus J25 means it is J2. J2. Next, what is the third row summation? Third row summation, y30, that number is 0. Some of the 4 elements in this third row will be 0. What is the summation of the fourth row? Y40 is minus J2. Y40 number is minus J2. Okay, simple. Tell me, I don't have shunt element at bus 3. That is one clarification. No shunt element at bus 3. Bus 1 we have shunt element, bus 2 as well as bus 4 also we have shunt element. See, admittance minus J. Admittance minus J means, is it inductive or capacitive? Is it inductive or capacitive? Admittance minus J means, is it inductive or capacitive? Inductive. So, the first shunt element what we have, so-called at bus 1, it is inductive in nature or is a reactive also? Inductive in nature. Whereas second one, plus J symbol, plus J, admittance plus J, capacitive in nature. Capacitive in nature. Whereas last one is again inductive in nature. Inductive in nature. So finally, the conclusion is at bus 1 and bus number 4, we have shunt reactors or shunt reactive elements. Shunt reactive elements. Whereas if you think about bus number 2, at bus 2, we have shunt capacitive element. Shunt capacitive element. Okay. At bus 2, we have a shunt capacitive element. Shunt capacitive element. Whereas at bus 1 and 4, we have a shunt reactive element. And you don't have any shunt element at bus number 3. No shunt element at bus number 3. No shunt element at bus number 3. Clear? So let's continue. So I'll take up next problem. Next one. So it's also a type of exercise problem to you. Exercise. Just go through it. So this is some data. It's a model in the examination generally. It's a type of model in the examination. Consider the following line data of a 3-bus power system network. Consider the following line data of a 3-bus power system network. Just read the data what they said. From bus number, to bus number, series impedance, total line charging admittance. Total line charging admittance. I'll come to that name. I'll come to that name. Bus 1 to bus 2. Series impedance 0.1 plus J0.2. Total admittance is J2. Shunt admittance total J2. Shunt admittance total J2. Then what you should do is that line what we have between 1 and 2, we have to keep in a pi model. That line what we have between bus 1 and bus 2, we have to keep in a pi model. Half of the shunt admittance at sending end side, half of the shunt admittance at the receiving end side. Means in the J2, J1 we should keep at sending end, J1 we should keep at receiving end. I will show that. I will show that. Just listen. Just listen. Next one. Bus 2 to bus 3. J0.4 series element, J3 shunt admittance. Bus 3 to bus 1. 0.2 plus J0.3 shunt element we don't have. Limit. 120 reference. 120 reference. J1. What is that? Shunt element. It's a shunt element. 220. Again we have a shunt element. Find diagonal elements of the Y bus. How many buses we have in the system here? 3 buses now. So diagonal elements of Y bus means we should calculate the values of Y11, Y22, Y2. Only these 3 numbers we have to calculate. That's it. Okay? Yeah. First, if it is a problem given of this manner, it is always better to draw the per phase model of the given system. Then we should find out Y11, Y22, Y33 and whatever the number it is required. So let us show per phase network of the from the given data. Per phase network from the given data. So I show bus 1 here. Bus number 2 I am showing here. And this is bus number 1, 2, 3 buses. 1, 2, 2, we have a series impedance 0.1 plus J0.2. 1, 2, 2. We have a series impedance 0.1 plus J0.2. Shunt admittance is J2. Shunt admittance is J2. Half at sending end side, half at receiving end side. Kindly observe this. See, admittance plus J. Look this one. I have to explain this again. Admittance plus J means what the nature? Inductive or capacitive? Admittance plus J means is it inductive or capacitive? Definitely capacitive. Yes or no? Impedance plus J. Look here. Impedance. Impedance plus J means it is inductive in nature. That's why I have shown the series impedance as R plus JX form. But shunt element is given in the form of admittance plus J. So I should show that as a capacitive element here. I should show that as capacitive element. Okay. So now you write these numbers. Simply I'll call Y1. Y1. Both numbers will be equal. Y1, Y1. The total is J2. So half we should keep here J1. Remaining half here J1. That's it. This is a way of modeling the transmission line. If the series impedance and shunt admittance are given. All of you, please listen. All of you, please listen here. Please listen here. If a line is consisting some series impedance and shunt admittance means we should keep that line in a pi model by keeping whole series impedance at one place and half of the shunt admittance at sending end side, half of the shunt admittance at the receiving end side. This is a way of drawing the pi model of the transmission line. Okay, let's move on. Bus 2 to bus 3. Again, we have some series element and shunt element. Bus 2 to bus 3. It's only reactive in nature. There is no resistance here between bus 2 and bus 3. Z23, that is J0.4. And total shunt admittance is J3. Total shunt admittance is J3. J1.5 sending end side, J1.5 receiving end side. We should at this place to keep right J1.5, and at this place again you keep J1.5. So I'll call this number Y2, J1.5, and this is Y2, J1.5. That's it. Okay, look back. 3 to 1, you have only series element and there is no shunt element. So 0.2 plus J.3, only series element you should add here. Moreover, it's an impedance. Series impedance we have to add is Z31, 0.2 plus J.3. Next thing, 1 to 0, shunt element at bus 1, J1. What's the nature of this? What's the nature? Is it inductive or capacitive? Shunt element at bus 1, is it inductive or capacitive? Total line charging is nothing but total admittance, shunt admittance of the network. That's it. Line charging admittance is nothing but shunt admittance of the network. Total in the sense, total admittance of the transmission line, shunt admittance of transmission line. Half of that you should keep at sending end side. Half of that we should keep at receiving end side. Tell me inductive. So 1 to 0, we should keep an inductive element of J1 impedance. 1 to 0, we should keep an inductive element Z10, that is J1. That is J1. Okay, next thing. 2 to 0 minus J0.5 means it's capacitive in nature. 2 to 0, you should keep this in capacitive nature, impedance only, but this is minus 0.5. Minus J0.5. Yeah, clear? I think it's done. Charging admittance means it's a capacitive nature only, shunt element of transmission line. See, very simple. You have to calculate diagonal elements of your Y-bus matrix. So you take bus number 1, bus number 2, as well as bus number 3. What are the direct elements connected to bus 1? How many elements are directly connected to bus 1? Number you tell me. How many elements are directly connected to bus 1? How many? 4. Total we have 4, right? So we have Z12 connection, Y1 connection, Z10 connection, Z31 connection. So sum of these 4 admittances is nothing but the value capital Y11. That's it. Okay. Yeah. Let's say in the next slide. Diagonal element capital Y11 equal to first admittance of this 10 element 1 by Z10. Plus you go in some round Z10. Next Y1 plus 1 by Z12, 1 by Z2, 1 by Z12, 1 by Z31. Okay, you keep these numbers. Z10 number how much? J1. Y1 number J1. Z12 number 0.1 plus J.2. And Z31 number 0.2 plus J.3. So 1 by J1 will be minus J1 plus J1 here. and you take the rationalization for the first and second numbers. Rationalization you should do from complex numbers. Like this, you should do 0.1 square plus 0.2 square plus 0.2 minus j 0.3 by 0.2 square plus 0.3 square. Yeah, you take the real and imaginary part separately. Take up the real part as well as imaginary part. At 1, why it is inductive? In what column they have given at 1? 1, 2, 0, it is given in impedance, right? Given in impedance form plus J. Plus J impedance means inductive in nature. Plus J1 series impedance 1, 2, 0. So that will be obviously inductive in nature. Yeah, calculate real part of this and imaginary part. Tell me anybody. It is coming 3.53 minus J 6.307. Getting this? These two will be cancelled anyhow. And you will get 0 here plus this number 1 by 0.1. So 2 minus J4. First number is 2 minus J4. Second number 1.538 or 54 you take minus J 2.31. So it will come 3.54 real part and imaginary part is minus J 6.71 per unit. 3.54 minus J 6.71 per unit. Do rationalization properly. Vasishtha, do rationalization properly. You get plus only in the denominator. Yeah, 6.31. 6.31. It's not 71. 31. Yeah. So let's continue with the Y22 calculation now. Y22 calculation quickly. Capital Y22. What you can say capital Y22? Sum of all admittances connected to bus 2. Can you tell me how many elements are connected to bus 2 directly? How many elements are directly connected to bus 2? 1, 2, 3, 4, 5. Total 5 elements are connected to bus 2. Admittance of all these 5 elements, summation is a value capital Y2. First one, 1 by Z20. 1 by Z20 admittance. Second one, Y1. Next one, 1 by Z12. Next one, 1 by Z23. 1 by Z12, 1 by Z23 plus Y2. 1 by Z20 number is minus J 0.5. Y1 number J1. Z12 number 0.1 plus J 0.2. Z23 number, if you see, J 0.4. And Y2 number is J 1.5. So if we do 1 by J 0.5 in the sense, it will be plus J2. And we have J1 already existing plus that number 1.5 I will add. So it will come 2 minus J4 already we have done in the previous case study, previous calculation. And this is minus J 2.5. Minus J 2.5. So real part will be 2. Imaginary part we have to do 2.5 cancel and it will come minus J2. That's it. 2 minus J2 per unit. 2 minus J2 per unit. Okay. Capital Y22 number 2 minus J2. Do the calculation of capital Y33 also quickly. capital Y33. How many elements are connected to bus 3? How many elements are directly connected to bus 3? 3 elements are there. First one, Z31, next Z23, next we have Y. Sum of these 3 admittances is the value capital Y3. Let me take. Admittance of Z31 is 1 by Z31. Admittance of Z23 is 1 by Z23. And we have one more admittance shunt Y. Okay. So you get 1 by, what is Z31? 0.2 plus J.3. And Z23 number, it is J0.4. And Y2 number is J1.5. So the first number, if you take up the inverse, you may get like 1.54 minus J2.31. 1.54 minus J2.31. And the second number minus J2.5. And you have next number plus J1.5. And you'll get minus J1. That's added to this 1.54 minus J 3.31. So this is a value capital Y3. 1.53 minus J 3.31. Capital Y3. See, particularly in the previous problem, what we have discussed. You can observe that the Y-bus matrix is a pure imaginary matrix. In the previous problem, what we have done, Y-bus matrix is a pure imaginary matrix. But now, in the present problem, what we are having, we are getting some real numbers also. Y-bus is consisting some real part also. Means what we should think here is, if the network is consisting resistances, definitely your Y-bus elements will be consisting real parts. If the network is completely lossless means there are no resistors in the network, then your Y-bus is purely imaginary matrix. Y-bus is a purely imaginary matrix. Okay, yeah, let's continue like this. If network consists resistances, then Y-bus will have real part. And if network is completely lossless, then Y-bus is a pure imaginary matrix. Y-bus is pure imaginary matrix. Y-bus is a pure imaginary matrix. So I think all of you getting this? See, bus 3, you have Y2 connection, right, Satish? You go through that network, what we have drawn. This is a network we have drawn, na? At bus 3, you have Y2 connection, right? Y2, 1 by Z23, 1 by Z31. Just follow the rule. Sum of all admittances connected to the bus 3. What are the admittances connected to bus 3? Take up them. Add all these numbers. That is nothing but capital Y33 value. Okay. See, from this problem, what we have learned is simply, first thing what we have learned is, if a transmission line is given simply with some series impedance and shunt admittances, we have to keep that line in a pi model. Half of the admittance, total line charging admittance, we should keep at sending end side. Half of the line charging admittance at the receiving end side. Okay. So, and then as we said, if the network is consisting resistances, your Y-bus elements will have real parts. If the network is consisting or network does not consist in a resistance, your Y-bus is coming as pure imaginary matrix. These are some simple conclusions we can draw from this problem. Okay. Yeah. So let's move to one more problem. With respect to Y-bus. You see this one. So it's from our classroom objective questions. Look at this. See, the Y bus of a 3 bus 3 line system. 3 bus 3 line is this one. J minus 14.4, 10, 5. 10 minus 11.5, 2.5. 5. 2.5 minus 6.8. All elements are J. Means, do I have any resistor in the network? Do I have any resistor in the network? Yes or no? No, because Y bus is a pure imaginary matrix here, so we don't have any resistance in the network. Next one. Each transmission line is represented by pi network. The shunt susceptance of the transmission line between the buses 1 and 3 will be how much? Shunt susceptance of the transmission line connecting the buses 1 and 2. See, we have to calculate shunt element of the transmission line 1, 2, 3 here. That's it. See, already he said all the transmission lines are represented in the pi network. First of all, from the statement what he said, we have 3 bus system, 3 lines. That I will show first. Listen here. 3 buses I am showing. Bus number 1, bus number 2, bus number 3. Okay, next. 3 lines. Look first. If you look at this Y bus, Y12 number non-zero, Y13 non-zero, Y23 non-zero, Y12 non-zero, Y13 non-zero, Y23 non-zero. These 3 numbers are non-zero. Means we have 3 lines between the buses. So let me show. Bus 1 to bus 2, 1 line we have. Bus 2 to bus 3 we have 1 line. And then bus 1 to bus 3 also we have 1 line. Like this. Not only that, he said all the 3 lines are in the pi models. All the 3 lines are in pi models. So I have to keep shunt element for the line connected between bus 1 and bus 2. Like this. Generally, the natural shunt element of transmission line is capacitive. Natural shunt element of transmission line is capacitive in nature. Okay. So here also we should keep that shunt element. So like this, for each and every transmission line, there exists one shunt element. There exists one shunt element in this manner. Okay. 0 reference. Reference you can say. Next. Why we have taken only reactive elements means I don't have any real part in the Y bus. That's a simple reason we can say. See, what we have to calculate here is the shunt susceptance of the transmission line connecting buses 1 and 3. Between bus 1 and bus 3, we have one transmission line. This transmission line, shunt susceptance value we have to calculate. Let us take up the notations first. Listen, please. Listen here. Let us take up the notations. Bus 1 to bus 2, we have one transmission line Y. So this is having one shunt element Y1. This shunt element is also Y1. Because in the pi model, sending end side shunt element and receiving end side shunt element of transmission line will be equal. Of transmission line will be equal. Y1. Next, at this place, I will take Y2. I don't know the numbers. That's why I am assuming these things as Y1 and Y2. So this will be again Y2 equal. And here you assume Y3 and this will be also Y2. Clear? Next thing. See, I want to calculate the value of Y3. After calculating that Y3, 2 times of Y3, that is nothing but shunt admittance of line 1, 2, 3. So you write here, shunt admittance of line 1, 2, 3. Line 1, 2, 3 is nothing but 2 times of Y3 number. So that Y3 number we have to calculate. The shunt element we have to calculate. Okay. For example, just to answer this one to me, at bus 1, what are the shunt elements at bus 1? Only shunt elements at bus 1. Anybody? Tell me please. What are the shunt elements at bus 1? Only Y1 and Y3, right? Only Y1 and Y3. These are the shunt elements at bus 1. Sum of these two is a resultant shunt element at bus 1. Sum of these two is a resultant shunt admittance at the bus 1. Bus 2. What are the shunt elements existing? Y1, Y2. Sum of these two is a resultant shunt admittance at bus 2. Similarly, at the bus 3 also, we should say Y3 plus Y2. Y3 plus Y2. So this is a way how to write the net shunt admittance at bus 1, bus 2, bus 3 from the given network. So I write admittances of shunt elements at buses. Yeah, first I'll say at bus 1. At bus 1, I'll say Y10. Shunt admittance is Y10. That is nothing but Y1 plus Y3. Y1 plus Y3. Next, at bus 2, shunt element notation Y20. What are the shunt elements at bus 2? Y1, Y2. Y1, Y2. At bus 3, Y30, bus 3. That is Y30. What you can get at bus 3? Y2, Y3 summation. Y2 plus Y3. That's it. Okay. Now, already we have matrix, right? Already we have matrix. From matrix, you try to get the shunt elements because summation of first row will give Y10. Summation of second row will give Y20. Similarly, third row. Okay, I'll write from matrix. From matrix. First, you take up the Y bus given. Pick up these elements quickly. That is minus J14.4, J10, J5. Let's keep the same J10, J5. And this number minus J11.5, J2.5, J2.5, and it is minus J6.8. Minus J6.8. Okay, simple. What is the summation of the first row? Summation of first row is nothing but the value small y10. How much is that? J0.6. First row summation will be J0.6. Okay. Second row summation. Tell me now, what is that second row summation? Y20, you can say that will be minus J12.5. Sorry, plus J12.5 minus J11.5, it will be J1. What is the third row summation? Third row summation, Y30, what will you get now? It's J7.5 minus J6.3. I think you get minus plus J1.2. Plus J1.2. Are you getting this? Yeah. Plus J1.2. Like this will be. Then simply take up these equations what we have and match with these numbers. Y10 is Y1 plus Y3 from network, whereas from matrix it is J0.6. Match. Y1 plus Y2, J1. Y2 plus Y3, J1.2. Solve the three equations. Try to get the value of Y3. 2 Y3 is a shunt admittance of transmission. Okay? Yeah. Let's move ahead. Therefore, you can write Y1 plus Y3 is equals to J0.6. Y1 plus Y2 is equals to J1. Y2 plus Y3 is equals to, how much is that number? J1.2. J1.2. Now, you have to get Y3, right? So this is 1, 2, 3 equations you consider. 1, 2, 3 equations. Take up equation 1 minus 2. Equation 1 minus equation 2. What you can say from this? 1 minus 2 means you get y3 minus y2. Y1 will be cancelled out, y3 minus y2. And the difference is minus j 0.4. If you take equation number 4, then simply add 3 and 4. Add equation 3 and equation 4. y2 will be cancelled. 2y3 equals to j 0.8 means value y3 will come, of course, 2y3 we need now, j 0.8. That's it. I'll write the terms now. So shunt admittance of line connecting buses 2 and 3, buses, sorry, 1 and buses 1 and 3 is j 0.8. Yeah, so I'll write shunt admittance of line 1 to 3 is j 0.8 per unit. But actually in the problem is asking the susceptance value, right? Asking the value of susceptance. What do you mean by susceptance now? Susceptance will be by removing the j symbol. Susceptance is nothing but 0.8 per unit we have to answer, removing the j symbol, right? So you can say shunt susceptance of line connecting buses 1 and 3 is 0.8 per unit. This is the answer is 0.8 per unit. Clear? So our answer, we have to fill in that blank will be 0.8 per unit. 0.8 per unit. Fine. So let's say one more problem with respect to the Y bus. Take up this. Let me check once. Yeah, you go through this question. I'll come back within 2 minutes. Please go through this question. This one, a 3-bus power system has Y bus matrix as follows. Find modified Y bus by keeping a shunt capacitor bank of reactance 0.5 per unit at bus 3. At bus 3, he is asking us to keep one shunt capacitor bank. Shunt capacitor bank. Yeah. See this? So in this problem, already existing system Y bus is given. Already existing power network Y bus matrix was given. Let me write it once. It is minus J20. Let me copy better. So it is the existing system Y bus matrix. Existing system Y bus matrix. Right. See at bus 3, he is asking us to add one shunt capacitor bank. So this is some network you assume. Whatever we have, 1, 2, 3 buses, something, some network. And this is a bus number 3, which we are concentrating now. Bus number 3, which we are concentrating. See, at this bus 3, he is adding one additional shunt capacitor bank, something like this. Shunt capacitor bank we are adding. And what is the impedance of the shunt capacitor bank? He said reactance. How much is the reactance value? 0.5. Reactance value 0.5 means what is the impedance of capacitor? Minus J 0.5. Impedance of capacitor will be minus J 0.5. So this capacitor impedance is minus J 0.5. And how much is admittance of this capacitor now? Admittance of this capacitor is 1 by minus J 0.5. This will come to be J2 per unit. That will come to be J2 per unit. Clear? Which elements will change now? Which elements will change? Actually, you don't have any change in the off diagonal elements. That's for sure. Why it is so means off diagonal elements depends upon only interconnections. As you are not disturbing the already existing interconnections, off diagonal elements will be remains same. Diagonal elements, Y11 no change, Y22 no change, Y33 will change. Why in the sense we are adding the shunt element only at the bus 3. We are adding the shunt element only at the bus 3. So only Y33 value is going to be modified. Remaining numbers will be unaltered. Okay. Yeah. So I'll say in the next slide. Next slide. So because of this addition, only capital Y33 value will change. Only capital Y33 value will change. We don't have any change in the values of Y11, Y22 as well as the remaining elements of Ys. Remaining elements of Ys. Yeah. Only line charging admittance was split into 2, not this one. This is an intentional shunt element at bus 3. Intentional shunt element at bus 3. It's a different. Okay. Now, what is the definition of Y33 generally? Definition of Y33. Sum of all admittances connected to bus 3 directly. Sum of all admittances connected to bus 3 directly. Already some admittances are connected. And he said that summation as minus J18. Now, we are adding one more new admittance here, so-called YC. And what the resultant summation of admittances connected to bus 3 means that old value of Y33 what we have plus this new element what we have added, so-called the capacitor admittance. Right? So I can write capital Y33 new is nothing but capital Y33 old value plus this extra shunt element added at bus 3, that is YC. That is YC. Okay? Yeah. What is Y33 old? Y33 old minus J18. What is YC number? J2. So this number will come to be minus J16 per unit. Remaining elements are unaltered. So your new Y bus matrix will be like this. New Y bus matrix. We have a change only in this number. That will be coming as minus J18, sorry, 16, minus J16. So I think all of you getting this? Clear? It's not required to draw single line diagram, Dinesh. It's not required to draw single line diagram. I'll tell you when it is necessary to draw single line diagram. Simple, very simple thing. At any bus, if you are adding one extra shunt element, that respective diagonal element will change. What is that new diagonal element means? That old value, whatever is existing, plus newly added shunt element admittance. Newly added shunt element admittance. Okay, let's move ahead. Let's move. So one more problem I'm taking up. Just observe now. Look this one. Look this problem. See this. The following matrix gives Y bus of a 3-bus system. The transmission line model is shown in the figure. Added between buses 2 and 3 newly. Find modified values of capital Y22 and capital Y33. Modified values of capital Y22 and capital Y33. Simple question. Already existing network, we have something which they have not given, but they have given Y bus of this one. Okay, now between buses 2 and 3, we are adding this element, so called this model newly. Transmission line, okay, is at the transmission line model that is adding. After making that addition, what will happen to the values of capital Y22 number as well as capital Y33 number? Clear? Okay, first, let us say, look here, all of you. Look here. Yes, anonymous attendee. Just look here. This is some power network we have already existing. Taking up buses 2 and 3. Taking up only buses 2 and 3. This is bus number 2. And this is bus number 3. Bus number 2 and bus number 3. Now, we are adding this what we call pi model between these two buses 2 and 3. Let us take first of all, listen here. You have a series element of J0.5 and shunt element of J0.5. Series element J0.5, moreover it is inductor. What is the nature of the J0.5 now? Is it in the form of impedance or admittance? Inductor plus J. Inductor plus J means what form? Impedance or admittance? That will be in the form of impedance. Okay. So series element he has given in the form of impedance. Shunt element he has shown capacitor. But they said plus J. Capacitor plus J symbol. What is the nature of that? Admittance or impedance? Shunt element is in the form of admittance in the problem given. That identification we should make before going for connection or anything. Okay, right. So let me show that model between bus number 2 and 3. This is one inductor element you have, and this is a capacitor element in the shunt mode, pi model. Okay, see, inductor plus J0.5 in the sense it is in the form of impedance. So I can say Z23 number J0.5 per unit. Next one. Shunt element capacitor plus J. Capacitor plus J means it is in the form of admittance. So you can call this one Y, or you say Y1, whatever it is, Y1. Some symbol you take according to your view. This is J0.5. This is also J0.5. J0.5. Okay. How admittance means I explained the same thing till now. Capacitor impedance will be minus J symbol. Admittance will be plus J symbol. In the question, they have given plus J 0.5 for the capacitor. Plus J 0.5 for the capacitor means it is in the form of admittance. Inductor impedance is in the form of plus J. In the problem, they have given plus J 0.5 for the inductor, means this number is in the form of impedance. That's it. Okay, let's continue. Let's continue now. You have to calculate modified values of capital Y22 and capital Y33. What do you mean by capital Y22? What do you mean by capital Y22? It is sum of all admittances connected to bus 2. Sum of all admittances connected to bus 2. See, actually, before adding this line, already some admittance are connected to bus 2. Already some admittance are connected to bus 2. That summation will be given by this Y22 volt. Yeah, this minus symbol is missing in the question. Minus symbol is missing. Yeah, let me repeat. Minus J 4.5, what you have here, Y22 volt number. Y22 volt number is nothing but summation of all admittances connected to bus 2. But now we are adding this network newly. What are the additional elements to be added to bus 2? One is Z23, next number is Y1. So you have to add these two numbers to the Y22 volt existing. Y22 volt existing. By that way, we can get the value of Y22 new number. So all of you getting this? Please tell me. All of you getting this one? Very simple thing. So I can say Y22 new is nothing but Y22 volt value plus Y22 volt value plus Y22 volt is there in the network. Now we have to add some more shunt elements, or some more elements, not shunt elements, some more admittances directly connected to bus 2. One value is Y1, next value was 1 by Z. One value Y1, next value was 1 by Z23. Simple. What is Y22 volt number? What is that Y22 volt number? Minus J 4.5. And what is the value of Y1? It's not shunt element, Vasistha. Have I said this is a shunt element? Z23 connected between bus 2 and bus 3. How can it be a shunt element? Have I said it's a shunt element? It's not shunt element. That's the element connected to bus 2. We have to add that to Y22 to take up the Y22 new number. That's it. Yeah, good. So Y1 number that is J.5 plus 1 by Z23 number we have J 0.5. So this if we calculate, it is minus J4 summation of these two, and this minus J2, this number will come minus J6 per unit. Minus J6 per unit. Clear? Similarly, what is the value of Y33 new number? What will be the value of Y33 new number? Y33 new. Just observe now. Again, you should say Y33 old value what we have already. Y33 old value what we have already. Plus this new additions what we are making. Y1 and then 1 by Z2. Admittances, right? Y1 plus 1 by Z2. I think Y33 old is minus J5 plus Y1 number J 0.5. And it is 1 by J 0.5. So it is minus J2. So it is minus J 6.5 per unit. Minus J 6.5 per unit. Yes, Manish. Yes, I will discuss about that also, Manish. Okay, you please tell me how many elements will modify in the Y bus in this case? In this case of line addition, how many elements in the Y bus are going to be modified? Already we are observing Y22, Y33 are changing. Other than these two, which elements will change? Y23 will change, as well as Y32 also going to be changed. So total 4 elements are going to be modified in the Y bus. Okay, if you want to write this, in this case, total 4 elements in Y bus will change. Y bus will change. 4 elements in the Y bus will change. Okay. So what are the 4 elements means? Y22, Y33, Y23, next number Y32. These are the 4 elements expected to change. Expected to change. Yeah. Next. What about that Y23 and Y32 new numbers? What will be the values of Y23 new number and Y32 new number? But see, actually, in the problem given, they have that Y23 old number 0, Y32 old number also 0. That's fine. That's okay. That's okay. But if already some value is existing in the old matrix, not 0, not 0. Some value was existing in the old matrix. Now we are adding this number newly. This number newly. If you want to calculate this small Y23 new number, okay, it is 1 by J0.5 means it is minus J2. If this is added newly between buses 2 and 3, then how will it be the modified value of capital Y23? That's the question. How will it be the value of modified capital Y23? I'll tell some procedure here. Kindly go through the thing. Go through the thing what I am saying. Some procedure. Look here first. Look here. Capital Y23 old value, we have something. Capital Y23 old value, we have something. That is nothing but minus Y23 old number, already existing admittance. Already existing admittance between the bus 2 and bus 3. Means obviously, small Y23 old is nothing but negative of capital Y23 old value, you can say. Small Y23 old is nothing but negative of capital Y23 old. Clear? Now, the question is, listen please. The question is, if you are adding this new element, so-called small y23 new between buses 2 and 3 newly, it will go in parallel with the already existing one. Now the question is, what is the resultant admittance connected between buses 2 and 3? Resultant admittance connected between buses 2 and 3 is nothing but Y23 old value existing, small Y23 old value existing, plus newly added admittance between buses 2 and 3, that is small Y23 new. Addition of these two is a resultant admittance existing between buses 2 and 3. Okay, so new admittance, or you say resultant admittance existing between buses 2 and 3 is nothing but small y23 old value plus small y23 new value. Small y23 old value plus small y23 new value. Now, you have to take negative of this whole number. That's the value. Capital Y23 new, or you can say capital Y32 new. Okay. So I'll say in the next slide. Capital Y23 new equals to negative of small y23 old plus small y23 new. Means it is minus y23 old minus y23 new. What is that minus y23 old? That is nothing but capital Y23 old minus small y23 new number. That's it. It is that new element in the Y bus matrix. New element in the Y bus matrix after making that line addition. In parallel, admittances, right? Admittances will get added if they are in parallel. Okay. See, if you want, you can calculate that capital Y23 new from the present problem. In the present problem, capital Y23 new is equals to capital Y23 old in the matrix given, that is 0 minus what is small y23 new number? Small y23 new number minus J2. So minus of minus J2, this number will come to be plus J2 per unit. And capital Y32 per unit also same as of Y23 new. So this will be again J2 per unit, you can see. capital Y32 and capital Y23 new, both are equal. That will be equals to J2 per unit. So total 4 elements are going to be changed in the Y bus matrix. So please complete it quickly. Yeah. So I'm showing previous slide. Y13 will not change, na? Y13. Who will decide Y13? Admittance between bus 1 and bus 3 will decide. Admittance between bus 1 and bus 3. That's not going to be changed. You are changing only the admittance between bus 2 and bus 3. Yeah. Good. If you want to rewrite that Y bus matrix quickly, just for your clarity, you can rewrite this matrix once. Yeah. So it's a modified Y bus new, you can say. These 4 numbers are getting changed. 4 numbers are changed. And this number you are getting like minus J6, I think. And this is J2. This is J2 minus J6.5. Like this, you will get the modified elements in the Y bus. Yeah. Next. We add shunt elements at bus 3 and bus 2, then Y22, Y33, 2 element change. Yes, correct. Correct. Yeah, let's take one more problem. Yeah. Okay. Before moving to this problem, listen here. I will discuss little about series compensation and shunt compensation to the transmission line. Series compensation and shunt compensation to the transmission line. These things will be even clearly discussed in transmission and distribution later. But for time being, for the sake of problems in the Y bus modification, I want to discuss about that, right? Series compensation and shunt compensation. Just look here. Series and shunt compensations to the transmission line. Shunt compensation to transmission line. To the transmission line. First, listen. Generally, if you think about natural pi model of transmission line, right? Pi model of natural transmission line without any compensation. Pi model of line without any compensation. Without any compensation. Just I am giving this model. You might have seen this model many times in this lectures only, right? Neglecting resistance for time being. So I will be showing this series reactance. And then we have some shunt element here. Shunt element is in the form of capacitor. Shunt element will be in the form of capacitor like this. Yeah, in this manner we. Okay, next thing. See, actually, the series impedance of transmission line, I will call this as JX line. Series impedance of transmission line, I am calling it JX line. Shunt admittance of transmission line, here we should keep half. And on the other side, we should keep remaining half. So it will be JB line by 2, JB line by 2, we should say. Okay. So this number will be JB line by 2, and this number is also JB line by 2. One more thing I am saying you, series element I kept in the form of impedance, shunt element I kept in the form of admittance. Series element we kept in the form of impedance, shunt element we kept in the form of admittance. Fine. Listen here. One simple word. See, compensation to the transmission line means, cancelling the already existing element. Compensation to the transmission line means cancelling the already existing element. What is the series element existing here? What is series element existing? Anybody tell me please. What is series element existing? Inductor. How to cancel that series inductor? We should add series capacitor. To cancel the series inductor, we have to add the series capacitor. So anywhere if you see series compensation to the transmission line means adding series capacitor. So I can say series compensation means adding series capacitor. Let's say the reactance of the series capacitor is Xc and percentage series compensation, if you write percentage series compensation, if you take, it is the ratio between series capacitor reactance to line reactance. Ratio between the series capacitor reactance to line reactance into 100%. Series capacitor reactance to line reactance multiplied with 100%. That is a percentage series compensation. Okay. Similarly, what do you mean by shunt compensation provided to the line? What do you mean by shunt compensation provided to the line? Tell me please. What is the natural shunt element of transmission line? What is the natural shunt element of transmission line? Capacity. Natural shunt element of transmission line is capacitive in nature. How to cancel it? How to cancel that capacitive in nature element? We have to add shunt inductor. Simple. To cancel the natural shunt element, natural shunt capacitive element, we have to add shunt inductor. So shunt compensation means you say adding shunt reactor to the transmission line. Adding shunt reactor to the transmission line. Generally, shunt element we keep in the form of admittance. Susceptance of reactor I am showing BR. It is susceptance of reactor. Susceptance of the shunt reactor we are showing it is BR. Now you write percentage shunt compensation. Percentage shunt compensation is equals to shunt reactor susceptance by natural susceptance of transmission line into 100%. Shunt reactor susceptance BR value by natural susceptance of transmission line. Yes, right. BR by B line into 100%. Okay, clear? Now, after providing compensation, both series and shunt, let us say, both series and shunt, how the transmission line looks, means model, how it is going to look, that will draw. Okay, so I will show in the next slide. Transmission line model with compensation. Okay, so simple. I will repeat the same model as it is. We are repeating, but I will show the changes what it is needed. Look here. So I am adding a series capacitor here. I am adding this series capacitor. Impedance of this series capacitor is minus JXC. Impedance of that series capacitor is minus JXC. Now, shunt reactor we have to add now. Shunt compensation. I should keep on both sides actually. I should keep on both sides. And this side will keep on shunt reactor of minus JBR by 2. Minus JBR by 2. And this side again we keep a shunt reactor of minus JBR by 2. Minus JBR by 2, minus JBR by 2. Because impedance of reactor plus J. Impedance of reactor plus J. Admittance will be minus J. So it will be minus JBR by 2 half on one side minus JBRBR to remaining half on the other side. That's it. Getting some clarity about the series and shunt compensations. Now, questions how we are going to solve further is after adding series compensation. After adding series compensation, how is a modified by this? After adding shunt compensation, how is a modified by this? Such type of problems we are going to take up further. Okay, so let's take the next problem. Next problem. Look this one. A 3-bus 3-line system has a Y-bus matrix as given below. This is a Y-bus matrix of a 3-bus 3-transmission line system. There exists a generator at bus 1. At bus 1, there exists a generator with series admittance value minus J2 per unit. Means we have a generator with its admittance minus J2. Okay, next. Line 1 to 2 is a short line model. He is saying line 1 to 2, you keep simple series impedance. There is no shunt element for the 1 to 2 line. Remaining 2 lines are nominal pi models. Okay, remaining 2 lines are nominal pi models. We should keep the shunt elements for remaining 2 lines. See the question what is asking exactly here. A 50% shunt compensation provided to the line 2 to 3. We have a line between 2 and 3 now. For that line, we are going to provide 50% shunt compensation. Find modified values of capital Y22 and capital Y33 elements in the Y-bus matrix. Find modified values of capital Y22 and capital Y33 elements of Y-bus matrix. Simple. Listen, please. Solution. Let's target on the requirement here. Let's target on the requirement. 50% shunt compensation we are providing now means the value BR by B line 0.5. 50% shunt compensation means BR by B line is equals to 0.5. Then what is the susceptance of shunt reactor to be placed? What is the susceptance of shunt reactor to be placed here? 0.5 times of B line. Susceptance of shunt reactor to be placed is 0.5 times of B line. Okay. What is B line number? What's the value of B line? We don't know. We have to pick up that B line from the data given. We have to pick up the value of B line from the data given. Means first what we should do is we try to calculate the shunt element of line 223 connected. Shunt element of the line 223 connected. For that purpose, definitely we should look into network and we should look into Y-bus and we have to get the number. Following the right. So I'll say line 223 shunt element calculation we have to do. Shunt element calculation we have to do. Line 223 shunt element calculation we have to do. Okay. First, let's look at this one. We have 3 buses. Let me draw network. Calculating the shunt element is possible only by the network. So it's a bus 1, bus 2, and I'm showing bus 3 now. Buses 1, 2, 3. At bus 1, we have a series admittance of minus J2. I'll add that. Minus J2 admittance means inductor or capacitor. Minus J2 admittance means inductor or capacitor. Inductor only. This is 0. This is minus J2 admittance. Inductor. Next one. Look at the data. Line 1 to 2 is a short line model. No real part. So it's a pure reacting network, you can say. Between 1 and 2, we have a short line model. So you have to keep that line simply with a series. Like this we should. Next one. 2 to 3, we have a pi model and 1 to 3 also pi model. Let me draw pi models here. 1, 2, 3. we are showing one pi model. 2, 2, 3. Also, we have to show one pi model like this. Like this way. Done. Next thing. Next thing. We have to find out modified values of capital Y22 and capital Y33. That's okay. First, what you have to calculate? What's our heading here? First, line 223 shunt element. This shunt element you have to calculate. Let's give these numbers or notations. We can say it is Y1, Y1, and you call it as Y2. Then obviously this number will be 8. What is shunt elemented bus 2 from network? What is the shunt elemented bus 2 from the network? Only shunt element. That's Y1, right? Only shunt element. Shunt element at bus 2. That's the value Y1. Okay, what is the shunt element admittance? What is the shunt element admittance from matrix? Because already he said matrix, right? So if you take up this matrix and second row summation, what you will get now? J2. Just write it if you want. Okay. So from matrix, Y20, take up this summation. That is J2 per unit. J2 per unit. And Y20 shunt element at bus 2 is Y1. So therefore, by doing this comparison, that Y1 number will be J2. Y1 number will be J2. Okay, now shunt element or shunt admittance of line 223 is equals to 2Y1. 2Y1 means it is J4 per unit. 2Y1. Shunt admittance of the line 223 is 2Y1. That will be J4 because we have Y1, Y1. So resulted will be 2Y1 you should say in the statement. So obviously the susceptance of this line 223 is 4 per unit. Susceptance of that line 223 is 4 per unit. Susceptance of the line 223 is 4 per unit. Now, providing compensation, so-called 50% compensation is saying, means BR by B line is equals to 0.5. From that, we have to find out the reactor susceptance, shunt reactor susceptance, right? Compensation. So, compensating shunt reactor susceptance. Compensating shunt reactor susceptance. Compensating shunt reactor susceptance. BR is equals to 0.5 times of B line number. We calculated this number 4. So this is coming as 2 per unit. So in the 2 per unit, half we should keep at sending end, half we should keep at receiving end side. So you have to draw the network with compensation. Network with compensation. Same network I am repeating. Same network I am repeating here. Like this we have. Just observe. I am adding the compensator on both sides. That's what we have discussed earlier. Let's clean this. I will keep the numbers in blue color. First, natural elements. Natural numbers I am keeping in blue color. Y1. You say here itself. Y1. Now we are adding this shunt reactor on one side. On the other side also, we are adding one more shunt reactor. Okay. And how much is this number? We should keep minus J BR by 2. That is nothing but minus J1. This number minus J BR by 2. That will be again minus J1. minus 0. Could you please tell me how many elements will be modified in the Y bus? How many elements will be modified in the Y bus after providing this compensation? With compensation, we are talking. With compensation, we are talking. How many elements? Only two. Only two elements are going to be modified, right? Not 3 or 4. Only 2. What are the 2 elements gets modified here? Y22 will change, definitely. Next number, Y33 is going to be modified. You don't have any change in the series connection between 2 and 3. So capital Y23 and capital Y32 will be remains as it is. Remains as it is. Okay. So let's say in the next slide. Next slide. Capital Y22 new number. Nothing but what you should say. Capital Y22 old value. Capital Y22 old value plus this minus j br by 2 should be added. What is capital Y33 new number? Capital Y33 old value plus this minus j br by 2 has to be added. That's it, simple. So this will be plus minus j br by 2. What is capital Y22 old value? How much? Minus j8. And this is minus j1. This number will come minus j9 per unit. And what is the value of capital Y33 new number? This is capital Y33 old value plus minus j br by 2. What is capital Y33 old number? Capital Y33 old number is minus j10. And you have minus j1. So this number will come to be minus j11 per unit. Capital Y33 new is minus j11 per unit. Okay. So you write here 2 elements in the Y bus got modified. Only 2 diagonal elements in this case. 2 elements got modified. The Y bus. And these are nothing but Y22 comma Y33. And you can take up the modified Y bus now. You can take up the modified Y bus. I'm repeating this matrix, what they have given, right? These are the 2 numbers got changed. So first number is becoming minus j9. Second number is becoming minus j11. That's it. Okay. So next, we'll take up one more problem. Please complete it quickly. Please complete it quickly. Right. Yeah. Go through this. Okay. Consider the following Y bus matrix of a 3-bus system. Consider the following Y bus matrix of a 3-bus system. Find modified Y bus matrix. Modified Y bus matrix with 30% series compensation provided for the line connecting the buses 1 and 2. Connecting the buses lines, connecting the buses 1 and 2. See, previous problem we discussed with respect to what we call shunt compensation. Now we are discussing with respect to series compensation. Yeah. So let's move. This is already existing network Y bus. Already existing network Y bus. Now you see. He is asking us to provide a series compensation to the line connecting buses 1 and 2. Series compensation compensation to the line 1, 2, 3. How much is that percentage series compensation is saying? 30%. He's saying that percentage series compensation is 30%. Okay, well and good, well and good. Just listen, just listen. See, you know already series compensation means XC by X line. XC is a series capacitor reactance. X line is a natural series reactance of line. This number will be 0.3. Means how much is the reactance of capacitor to be added? 0.3 times of X line. 0.3 times of X line will be the series capacitor reactance to be added. So before making this series capacitor addition and all, first you should know about X line value. First we should know about the X line value. To know about the X line, first of all, 1, 2, 3, what is series impedance? 1, 2, 3, what is the series impedance value? That we should get from capital Y13 number. Capital Y13 number. What is the capital Y13 number? J5. Okay, let me write in detail. From matrix or old Bybus, old network, you write. Capital Y13 is J5. And then what is small y13 value? What will be the value of small y13? Negative of capital Y13. Negative of capital Y13. It is minus J5. Then what is impedance of this? Impedance is nothing but 1 by minus J5. So it will come to be J0.2 per unit. 1 by minus J5, that number will come to be J0.2 per unit. Fine. Next, listen. So we have a series impedance between bus 1 and bus 3 as J0.2 per unit. Okay. Now we have to add series capacitor to that. After adding series capacitor, we get a modified series impedance between bus 1 and bus 3. Based on that, we should go for the modified Bybus. I think all of you getting these things. Can you move ahead? Right? So, line 1, 2, 3, series reactance value is 0.2 per unit. Therefore, series compensation or capacitor now, compensation reactance XC is a value 0.3 times of X line. So this will come to be 0.06 per unit. 0.06 per unit. Now, the modified connection of line 1, 2, 3. Modified line 1, 2, 3. Line 1, 2, 3. So we have some series reactor already existing. And we have a capacitor here. We have a capacitor. First of all, this series impedance of line is J0.2. And this is a capacitor we have added now. Capacitor we have added. And what is the impedance of the capacitor? Minus J0.06. Minus J0.06. And this whole number will come to be J0.14 per unit. J0.14 per unit between buses 1 and 3. Between the buses 1 and 3. Yeah. Line is a short line or medium line, that we no need to bother, right? Because we are concentrating only on series impedance here. We are concentrating only on the series impedance. So you no need to bother whether the line is a short line or medium line. Fine. Now I'll say Z13 new number is equal to J0.14 per unit. Now what is small y13 new number? Small y13 new is 1 by J0.14. Anybody tell me this number? 1 by J0.14. How much? Tell me please. So this will come to be minus J7.142. Minus J7.142 per unit. Small y13 new number. Now, what will happen to the capital Y13 new number? capital Y13 new number is nothing but negative of this, na? So it will come, you write better, minus small y13 new. So it will be plus j 7.142 per unit. Okay, so capital Y13 value was modified. Old value how much? Old value j5. Now the new number is coming minus plus j 7.14. Capital Y31 also same, j 7.14. So definitely capital Y13 will change. Capital Y31 will change. Not only that, capital Y11 will change. Capital Y33 also going to be changed. Total, how many elements are going to be modified in the Y bus? Total, how many elements are going to be modified in the Y bus? 4 elements are going to be modified in the Y bus in this case. Right? Very simple. Anywhere you modify the series element, definitely 4 elements are going to be modified in the Y bus. Okay? Yeah. So let's say, due to series compensation, 4 elements will be changed or will be modified in the Y bus. 4 elements will be modified in the Y bus. What are those elements means? Y11, Y33, Y13, Y31. Already we got Y13 and Y31. Now we should think about capital Y11 and capital Y33 modified. Capital Y11 and capital Y33 modified, we have to think now. Listen here. Capital Y11, capital Y33. All of you stop writing. Just look here. This is bus 1, bus 2, bus 3. Bus 1, bus 3. See, what is the resultant series admittance? What is the resultant series admittance between buses 1 and 3? That is minus j 7.142. Okay, capacitor is there. Capacitor was taken into the inductor, and resultant element is in the form of inductive. That's why I have drawn only inductor here. And what is that Y13 new number? That is minus j 7.142 per unit. Minus j 7.142 per unit. That's the value of small Y13 new number. Kindly listen. Don't confuse. This single element what we have, minus j 7.142, I will be redrawing into 2 parts. Bus 1, bus 3. First part, I will manage to get minus j5. Second part, I will be keeping that remaining number. How much is second part number? Parallel combination of 2 admittances. First part, I am making it as minus j5 intentionally. I'll tell you why. What is the second part number? All of you. What is the second part number? Minus j 2.142. Then only the resultant parallel combination will come to be minus j 7.14. Minus j 7.14. Fine. Good. Listen. See that minus j5 is a Y23 volt, right? Minus j5 is nothing but small Y23 volt. You can observe here. Y13. Small Y13 volt value is nothing but minus j5. So I can say this as small Y13 volt number. Now you can understand this problem in this way. Listen. How many of you will understand this? Try to get this one. Adding the series capacitor to the line 1, 2, 3, gave some resultant admittance. That we divide into 2 parts connected in parallel. One admittance I managed to have a volt number, and we have taken the remaining number here minus j 2.14. Simply adding the series capacitor is nothing but adding an interconnection between bus 1 and bus 3 with a number minus j 2.142. Can I say? Adding an interconnection between bus 1 and bus 3 with a number minus j 2.142. Can I say yes or no? Yeah, simple. Yes, series capacitor is added. After adding series capacitor, we have taken the resultant network that I am modifying into two parts in parallel. First part, I managed to have a whole number. New part added is minus j 2.14. Means I can say simply, I am adding a new admittance between buses 1 and 3 with a number minus j 2.142. That's it. So I'll say in the next slide, same diagram I will draw. Same diagram I'm drawing. Look here. Okay. This is a old network. This is a old network, right? Minus J5 also I pushed into old. Minus J5 also I have pushed into old. We are splitting that into two parts. According to our convenience in the what we call calculation. Could you please tell me now? Could you please tell me what is Y11 new number? What is Y11 new number? Sum of all admittances connected to bus 1. Already some admittances are connected to bus 1. That summation is Y11 old. Y11 old plus this new element we are adding, na? New element we are adding, right? So you take this small y new. That's it. Getting this one. Then where is that minus J5? Why you have not taken this minus J5? Because that's already there in Y11 old. That minus J5 already it is there in Y11 old. That's why I have not taken it specially. Y new we have to take. What is that Y11 old number? Y11 old number, it is minus J20. So it is minus J20 and this is minus J 2.142. So it will come minus J 22.14. 22.14. So I can say Y33 now. Y33 new equals to Y33 old value plus Y new. Okay. What is Y33 old value? Y33 old value, look back into the matrix, that is minus J12. Minus J12. And this Y new number is minus J 2.142. And this will come like minus J 14.14. Minus J 14.14. So total 4 elements got modified. We have shown all these 4 elements in the matrix. Okay, so let me rewrite this matrix, the modifications. So capital Y11, modified to minus J 22.14. Minus J 22.14. And capital Y33 was modified. It is minus J 14.14. Next one. These numbers are plus J 7.14. This number plus J 7.142. This is also plus J 7.14. So like this, we will get the modified Y bus after providing the series compensation. So till now we discussed about modification of the Y bus elements, Y bus matrix with different ways, right? So now we are going to conclude. How many elements got modified in the Y bus because of some addition or some removal. Okay. Similarly, Z bus also will make the comment at the end. So let's say in the next slide, a small table. Modification in the network. Okay. So number of elements changed in Y bus. Number of elements changed in Y bus. Okay, next, number of elements changed in Z bus. Number of elements changed in Z bus. Changed in Z bus. So just have a look. First, modification in the network. I'll say, look here. First modification I'm saying, generator addition or removal, whatever it is. Generator addition or removal. How many elements will be changed in the Y bus? Next, line addition or removal. Addition or removal. How many elements will change in the Y bus? Next thing, shunt element addition at a bus. Shunt element addition at a bus or removal also you can say. Addition at a bus. Next thing, series compensation to the transmission line. Series compensation to line. Next one, shunt compensation to the line. Shunt compensation to the transmission line. Series compensation to the line. Shunt compensation to the line. Can you fill this table? Yeah. First one. By the addition of this generator, it will be a shunt element at a bus, right? Shunt element at a bus means only one element is going to be modified in the Y bus. Only one element will be modified in the Y bus. Line addition or removal, how many elements? Line addition or removal, how many elements? 4 elements, right? 2 diagonals and 2 off diagonals. 4 elements will change in the Y bus. Next, shunt element addition at a bus. Shunt element addition at a bus. How many elements? Only one. Shunt element addition at a bus, only one element will change. Series compensation to the line. Series compensation to the line. Just now we discussed, na? How many elements will change? 4. 4 elements will change. Shunt compensation to the line. We have discussed it just now. How many elements? Sending end side, one shunt element. Receiving end side, one shunt element. Because of shunt compensation to the transmission line wire, I can say 2 elements will change. 2 elements will change. But whereas in the Z bus matrix, all elements are going to be modified if you make any variation. Whether it is a major change in the elements or minor change in the elements, that is immaterial to me. All the elements in the Z bus will be modified irrespective of the modification what you are making. Any modification you make in the network, definitely all the elements in the Z bus are going to be changed. All the elements in the Z bus are going to be changed. Clear? So this is about direct inspection method. So have a break for 10 minutes. We will continue up to 12:30. We will be continuing up to 12:30. Have a break for 10 minutes. After break, I will take up the singular transformation method. Just I will explain about that method and we'll do one problem on that. Then we'll move on to Z bus. Right? Z bus and some problems with respect to Z bus also we'll discuss. Yeah. 10 minutes break. 10 minutes break. We'll take up to 12:30. So I have resumed audio, video on screen. So let's continue. The next method of Y-bus construction, that is singular transformation method. Singular transformation method to construct the Y-bus. Yeah. See, by this singular transformation method, no, I'm not looking at the derivation here. I'm not looking at the derivation. Directly, I will tell you. Directly, I'm going to tell you how we are going to get this Y-bus matrix by singular transformation method. Just look here. Y-bus matrix will be like A transpose into Y primitive into A. A transpose into Y primitive into A. Like this we will have. I will explain about these matrices clearly. What that matrix A, Y primitive and A transpose. This matrix A is going to be called as reduced bus incidence matrix. Reduced bus incidence matrix. I'll tell you briefly how to construct this matrix and all. Reduced bus incidence matrix. And Y primitive, what we have there, this is going to be called as primitive admittance matrix. Primitive admittance matrix. Admittance matrix. Right? Y primitive is going to be called as primitive admittance matrix. Fine. Generally, the size of this matrix A, reduced bus incidence matrix, will be of number of branches by number of buses in the system. Number of branches by number of buses. That is the size of matrix A, reduced bus incidence matrix. Whereas primitive admittance matrix will be of the size number of branches by number of branches. Number of branches by number of branches. That will be the size of the Y primitive, we can call Y primitive. Okay. Yeah, let's take. Look here. What is that A transpose size now? Matrix A will be n branch by n bus. Na? Then what is the A transpose size? N bus by n branch. N bus by n branch. That's the size of matrix A transpose. What is the size of Y primitive? Y primitive. N branch by n branch. N branch by n branch. N branch by n branch. And what's the size of A? N branch by n bus. I think that multiplication will be possible to do. A transpose by primitive, n bus by n branch by n branch. So the whole matrix, these two product will come n bus by n branch. N bus by n branch. That multiplied to this will give n bus by n bus. That will be the size of the Y bus matrix, obviously. Just go through the matrix multiplications. Go through the matrix multiplications. You will get this size as n bus by n bus finally. Now I want to tell you how we can construct that matrix A as well as that Y primitive. These two things we will discuss. For that purpose, first I will take one network graph, number of nodes with some branches I will take. Okay. So I'm taking some example to explain about this. Some example. We are taking to know about that matrix A and Y primitive. This is a network graph with some nodes. 1, 2, 3 nodes I have shown. And it's a reference node 0. Reference node 0. These are some connections here existing. In this manner, we have some connections existing. Like this. Fine. Now I will give these branch numbers. These are nodes. Node numbers 1, 2, 3. Number inside the circle is indicating node number. Number inside the circle is indicating node number. Branch number I will keep simply like this. 1, 2, 3, 4, 5 branches. So it's a 3 node 5 branch network. 3 node 5 branch network. Yeah. First we want to take up matrix A. Matrix A construction. What is the size of that matrix A? Number of branches by number of buses, na? Number of branches by number of buses, right? So this side we should give the branch numbering, and this side we should give the bus numbering. Bus numbers I am showing. Bus number 1, bus number 2, bus number 3, 0. Buses 1, 2, 3, 0 on one side. Branch numbering I am giving 1, 2, 3, 4, 5 branches. 1, 2, 3, 4, 5 branches. 1, 2, 3, 0 buses. Yeah, it's very simple to give this matrix. Very simple to give this matrix. Just listen to my words. Standard node number 1. Standard node number 1. See, to fill this matrix A, I should give directions of current flows. I should give the directions of the current flows. After giving those directions, we are going to call that graph as oriented graph. Oriented graph. We are going to name this by giving some directions of the currents. You can take these currents on your own way, no issue. You can take these currents on your own way. Yeah. So now by standing at node 1 is in touch with how many branches? Branch 1, branch 2, branch 5. Branch 1, branch 2, branch 5. It is not in touch with 3 and 4, na? So 3 and 4 corresponding numbers we should keep 0. 3 and 4 corresponding numbers we should keep 0. Yeah, next one. Branch 1. See, this is one notation you have to follow. If current is leaving out from the node, you take it as positive 1, plus 1. If the current is entering into the node, you take that as minus 1. For example, I'll say at node 1 I am standing, branch 1 current is entering, so I will take minus 1 for branch 1 at node 1. I'll take this number as minus 1. Getting this? Now, branch 2 current at node 1, branch 2 current leaving out means I should call this one plus 1. Branch 2 current is leaving out, so it is plus 1. Branch 5 current also leaving out, plus 1. That's it. Next, standard node 2. Which are the branches connected to node 2? 2, 3. So only 2, 3 we should take. Remaining branches are not connected means 0. You see, branch 2 current entering into node 2, so it will be minus 1. Branch 3 current also entering into node 2, so this will be also minus 1. Very simple way of doing the construction. Okay, let's stand at node 3. Which are the branches connected to node 3? 2 branches are there, 4, 5. How are these currents? Entering. Only 4, 5 we should take, 4, 5. Remaining numbers will be zeros. How is the 4th branch current? Entering into node 3, so it will be minus 1 here. 5th branch current also entering into node 3, so it will be also minus 1. And whereas 0 reference you can talk, 1, 3, 4 leaving out. 1, 3, 4 leaving out, and remaining numbers are zeros. If the current is leaving out from the node, we should take that as a plus 1 symbol. Right? Like this, we should say plus 1 symbol. So this is that matrix A. But actually, this matrix we are going to name as bus incidence matrix. But what matrix we need actually? Reduced bus incidence matrix we need, na? Reduced bus incidence matrix means we should remove the column corresponding to the reference node. Means this reference node column we have, na? This you remove, and whatever the remaining portion of matrix you have, that we have to call as reduced bus incidence matrix. Okay, so I'll say this one. This we are going to name as reduced bus incidence matrix. Reduced bus incidence matrix. incidence matrix. Reduced bus incidence matrix. Okay, actually this is a A. I am calling this is some A1 because A is a notation I am using for bus incidence, reduced bus incidence matrix, right? So that's why I am calling this bus incidence matrix as A1. Reduced means after removing column corresponding to reference node, I'll call that as reduced matrix. Simple. Next one, let's look at the Y primitive admittance matrix construction. This is inversion of the Z primitive. Primitive admittance matrix, Y primitive is inversion of Z primitive. Y primitive is an inversion of the Z primitive matrix. And what is the size of this matrix? We said now, number of branches by number of branches. But in the present problem, what we are discussing, we are having a 5-branch system, right? 5 branches we have. So obviously the size of Z primitive will be 5 by 5. Z primitive will be 5 by 5. Let me write now. Z primitive matrix here is equal to, it's a 5 by 5 matrix I am showing. Five by 5 matrix I am showing here like this. Just observe what I am saying you. Just observe here. Very simple thing to write. Just answer this one. 1, 1 we have. 1, 1. So branch 1, branch 1. Branch 1, branch 1. That is self-impedance of the branch 1, we should say. Self-impedance of the branch number 1. 1, 1 means self-impedance of branch 1. 1, 2. Mutual between branch 1 and branch 2. Mutual between branch 1 and branch 2. 1, 3. Mutual between 1 and 3. 1, 4. Mutual between 1 and 4. 1, 5. Mutual between 1 and 2. Okay. Self-impedance of branch 1. Mutuals between 1 and 2, 1 and 3, 1 and 4, 1 and 3. Similarly, if you think about that column, that will be same as row, right? So you can call here ZM21, ZM31, ZM41, ZM51, but numbers will be same. Numbers will be same. Okay, what is this here? Self of branch 2. Self of branch 2. What is this one? Mutual between 2 and 3. This is mutual between 2 and 4. This is mutual between 2 and 5. And similarly, here also you get mutuals. What is this one? 3, 3. Self of 3. Self of 3. And these are mutuals. What is this? Self of 4. Mutuals. Self of 5. That's it. Simply in this Z primitive matrix, diagonals will be having self-impedance of the branches. Off diagonals will be having mutual impedances between the branches. Okay, right. Z primitive will have diagonals as self-impedances of the branches. Self-impedances of branches. And then off diagonal elements, off diagonals have mutual impedances between the branches. Mutual impedances between branches. Mutual impedances between the branches. And after getting this Z primitive matrix, take up the inverse of this. Okay. After taking inverse, you are going to get this matrix as Y primitive. Then we should move into the Y bus construction by using a formula A transpose into Y primitive into A. A transpose into Y primitive into A. Right? Clear? Next, I'll take up one small problem on this one. Small problem on this. just to give clarity about this method, I'm taking this problem. Just go through it. Consider the following three-bus system with self and mutual impedances indicated in the per unit form. Self and mutual impedances indicated in per unit form. Self impedance Z1, J0.4. Self impedance Z2, J0.3. Mutual between these two branches, J0.1. Find capital Y23 in the Y bus matrix. Find the value of capital Y23 in the Y bus matrix. Simple. How much is capital Y23 number? How much is capital Y23 number here? This is bus 2 and bus 3. This is bus number 3. And this will be bus number 2. Right? Bus 2 and this is bus 3. Tell me please, what is capital Y23 in this case? See, actually, you observe that we don't have any direct connection between buses 2 and 3. You can observe that we don't have any direct connection between buses 2 and 3. You might be expecting to give an answer as 0. You might be expecting to give an answer as 0. But you see, how you are saying Y23 equals to 0 means by direct inspection method. By the direct inspection method. But there is one limitation on the direct inspection method, that is, it can be applicable only on the networks which does not have any mutual impedances between the branches. If you don't have mutual impedances between the branches, then only direct inspection method can be applied to find out the Y bus elements. That's a limitation. But if you have mutuals or if you don't have mutuals, in any case, this singular transformation method is going to give the Y bus matrix perfectly, right? So I want to write that statement first before moving to this problem. Direct inspection method. Inspection method can be applied only if there are no mutuals. If there are no mutuals between the branches, okay? Between branches. But the method what we have proposed now, so-called singular transformation method, see, this method can be applied in any case, with mutuals as well as without mutuals, right? Can be applied in all cases, either with mutuals or without mutuals. With mutuals, or you can say without mutuals. Without mutuals. In any case, it will be applicable. Singular transformation method. So as we have mutuals here, the statement what we should say is, as we have some mutual linkage between branch 1 and branch 2, I can't apply the direct inspection method. So only one choice for you now. We have to do this problem only by using singular transformation method. But by using the singular transformation method, you can't find out only one specific element. It's not possible to find out only one specific element what we need. In that situation, we should do the complete Y bus construction, and then we should pick up the element capital Y23 properly. Okay, so this problem we have to solve by using singular transformation method. So as you know, by singular transformation method, bus admittance matrix is nothing but A transpose into Y primitive into A. A transpose into Y primitive into matrix A. Okay, what is that matrix A? To find out that matrix A, first you have to draw the network graph. Okay, draw that one. Network graph. 3 nodes we have. Node number 1, node number 2, node number 3, and you might be having some reference they have not shown in the figure. That may be ground or neutral point as a reference, which they have not shown in the problem. Okay. 1 to 2 we have a branch. 1 to 3 also we have a branch. Just observe. 1 to 2 we have a branch. 1 to 3 also we have a branch. Not only this graph, we need oriented graph. We need the oriented graph. Kindly observe, kindly observe. If the oriented graph needed to you, we should take up the directions of the currents in a proper way. Because we have some mutual linkages, right? Between the branch 1 and branch 2, and dot symbols also shown here. Dot symbols. See, simply what you feel is between 1 and 2 we have an inductor, you say. Between 1 and 3 also we have an inductor, you can take. 1 and 2, 1 and 3 we have some inductors. And these are the dots mentioned here. This is one dot, these are other dots. We have to follow this scenario. You have to follow this scenario simply. Take up the current in the same direction of dot. For example, in the first branch, 1 to 2 branch, if you take current in this direction, first it is entering into dot and then into winding. Dot and then winding. The second branch current also should be in the similar way. Should be in the similar way. Then only whatever the ZM we have taken in the problem, given in the problem, that will act as positive number. That will act as positive number. So if you take in this direction, then mutual impedance between these two will be J0.1. For example, if you take any one of these two currents in reverse, then we should take ZM value negative J0.1. That's the rule what we have to follow. All of you getting this point? Tell me please. For example, in the same thing, I'll show you. Same network I will repeat. This is 1. Okay, this is node 2. And this is one more inductor of line, node 3. I am showing dots here. Showing these dots. First one current I am showing in this direction, but second one current in opposite direction I am showing. So in this case, mutual impedance you should take as minus J0.1. Mutual impedance you should take as minus J0.1. Any one you have to follow among these two for this problem. All of you getting this or not? Please tell me. Please tell me, are you getting this? So I will be considering the current as in the first one. I will be considering the current as in the first one. So this is the orientation I am taking for this graph. This is a oriented graph. This is the oriented graph. Let's continue. Take up the matrix A. Then we will go for Z primitive and then Y primitive. Then we will go for the Y bus. Yeah, matrix A. Matrix A we want to take up. It is number of branches by number of buses. How many buses we have? 3 buses. Removing reference. Already we have removed the reference from the study. Branches 1, 2. 2 branches. You take the first. This is a branch 1 and this is a branch 2. Branch 1, branch 2. Okay. Next. Node 1 you stand. Node 1. Both branches are connected. Node 1. Both branches are connected. And current is leaving out from the node. Leaving out from the node into the branches. So it will be plus 1, plus 1. Plus 1, plus 1. Node 2 is stand. Node 2. Node 2. Branch 1 current entering. Branch 2 is not connected. Branch 1 current is entering. So it will be minus 1 here. And branch 2 is not connected. Node 3. Node 3. Branch 2 current is entering. Branch 2 current is entering. Branch 1 current or branch 1 is not in touch with node 3. Like this, we will get the matrix A. Reduced bus incidence matrix. Okay, fine. Z primitive. So called primitive impedance matrix. If you take Z primitive. So we have to take branches here. 1, 2. Here also you should say 1, 2 branches. 1, 2 branches. And 1, 1 means self impedance of branch 1 you should say. 1, 2 means mutual between 1 and 2. 2 to 1 mutual between 2 and 1. 2 to 2 self of 2. Keep these numbers quickly. Keep these numbers quickly. What is Z1? What is Z1 number? J0.4. Mutual between 1 and 2. J0.1. This number is again J0.1. Z2. How much is Z2 number? J0.3. So branches 1 and 2 you can take if you want. It's a Z primitive. Take the inverse of this matrix and you will get Y primitive. Take inverse of this one, you will get Y primitive. Get this, please. Primitive admittance matrix. Inverse of Z primitive. Inverse of Z primitive. So it's a 2 by 2 matrix. Na? First to take the J out. J you take out. J inverse you take. And then inverse of this real matrix you can get. Inverse of the real matrix you can get. Inverse of the real matrix. Yeah. So let's rewrite. J inverse means it's 1 by J. 1 by J means minus J. Minus J. Y primitive is minus J into this inverse, it is 1 by 0.4 into 0.3 minus 0.1 into 0.1. That's a determinant of this 2 by 2 matrix. And here you can have 0.3, 0.4. Diagonals are exchanged. Half diagonals will give will get negative sign, minus 0.1, minus 0.1. Minus 0.1, minus 0.1. And if you calculate this, it's minus J, okay. And this number is 0.12 minus 0.01. It will be 0.11. 0.11. And you have 0.3 by 0.11 means it will be 30 by 11. 30 by 11. And this will come to be 10 by 11 and 10 by 11 and 40 by 11. With the respective symbols, I will show it. First number is minus J 30 by 11. Second number will be plus J 10 by 11. Next number will be plus J 10 by 11. Next number will be minus J 40 by 11. Minus J 40 by 11. Like this you can. This is Y primitive. Getting all of you? Y primitive. Now you take up A transpose into Y primitive into A. First you take A transpose into Y primitive first. That you multiply with A and we will get the resultant matrix. But we have to pick up only the value of capital Y2. We should pick up only the value of capital Y2. Yeah. So let's move in the next slide. I'll say directly Y bus matrix. Y bus matrix. Let's call A transpose first. A transpose. What that A? Matrix A is okay. A transpose means 1, 1, 1, 1, minus 1, 0, 0, minus 1. It is A transpose. Y primitive, this one. Y primitive. Into A. Into A we will take in the next step. Matrix A will take in the next step. Yeah, you multiply these things quickly. So it will come to be minus J 20 by 11. First number, multiplication. Second number will come minus J 30 by 11. Next number it is J 30 by 11. Next number it is minus J 10 by 11. Next number it is minus J 10 by 11. Next it will be J 40 by 11. Like this you will get that A transpose into Y primitive. A transpose into Y primitive. Now you have to keep that matrix A 1, 1, minus 1, 0, 0, minus 1. You take up this multiplication and you will get the resultant matrix. And from that you should pick up only capital Y23 number. Capital Y23 number only we should pick up. But anyhow, if you want, you write the whole matrix. First number will come minus J 50 by 11. Second number is J 20 by 11. Next number J 30 by 11. Next number J 20 by 11. Next number you get minus J 30 by 11. Next number you can say j 10 by 11. Next we have j 30 by 11. Next it is j 10 by 11. And the next number is minus j 40 by 11. Minus j 40 by 11. This is a Y-bus matrix you can expect. And you should pick up only capital Y23 number. Pick up only capital Y23 number. Y23 number in the sense this plus j 10 by 11. Plus j 10 by 11. Plus j 10 by 11. Yeah, please complete it. Once after completion, please raise your hands. So I can say capital Y23 is equals to j 10 by 11 in the sense you get j 0.9091 per unit. J 0.9091 per unit. Capital Y23 number. Capital Y23 number. Okay, now could you please tell me in this particular case, just by looking at the network, you say we don't have direct connection between buses 2 and 3. We don't have direct connection between buses 2 and 3, but the capital Y23 number is coming non-zero, right? Capital Y23 number is coming non-zero. Now tell me, in this case, whether the Y-bus matrix representing the direct connectivity or not. In this case, whether the Y-bus matrix representing the direct connectivity or not. No, it won't represent the direct connectivity in this case. Okay, so I'm writing the statement. If there exist mutual impedances between the branches, between branches, right? There will be the Y-bus matrix will not represent the direct connectivity. Y-bus matrix will not represent direct connectivity between the buses. Direct connectivity between the buses. Direct connectivity between the buses. Clear? Definitely. Without mutual impedances, you calculate the Y-bus by direct inspection method, or you calculate Y-bus by singular transformation method. It will come identical. No issue. It will come identical. Okay, if I ask one general question to you, just tell me tell me your answer in a general way. Y-bus matrix represents the direct connectivity or not? Y-bus matrix represents the direct connectivity or not? That's the question. Yes or no? Tell me, please. You should say yes. Listen to me. You should say yes. It will be representing the direct connectivity, you should say. But if they ask you again, will it represent always? No. In some cases, it won't represent the direct connectivity. When in the sense, if you have some mutuals between the branches. Following all of you? Generalized answer will be yes. But in special cases of mutual impedances between the branches, it may not represent the direct connectivity between the nodes, right? So we'll stop the class at this point. In the next class, we will discuss about Z-bus little bit, and then we will complete the load flow analysis. Okay? Load flow analysis, mainly we concentrate on Newton-Raphson method, Jacobian matrix, these things only, right? In the view of examination. So you can raise your hands if you have any doubt. Vijay. Tell me, Vijay. Vijay, do you have any doubt, Vijay?
Hello, sir. Am I audible?
Tell me.
Sir, in the last question, just now, while we were forming matrix A, in branch number 2, node number 3, that value should be 0, I think.
Branch number
Where
2,
it is
node number
plus
3.
1.
Branch number
Yeah.
2, node number 3 connected, right?
Branch number 2, node number 3 connected.
So it will be minus
Okay,
1 because
okay,
current
yes.
is entering.
Yes. Got it, sir. Thank you.
Yeah, yeah. Soundarya.
Hello, sir.
Tell me, Soundarya.
These are last two problems, sir. 93. Network phase once explains, sir, that
Which one?
93, sir. 93F, sir. 93F.
93, yeah. Okay. Tell me, what's the doubt you have in this?
1 to 2 and 1 to 3 buses are dot.
See,
I'm not
actually,
understanding that one.
they have given some dots in the question, right?
Okay, sir.
Yes or no? So you have to
Yes,
take
sir.
the current directions only according to the dot symbols.
Yes, sir.
See, I have taken first branch current direction in this manner. Means first I have taken the current direction such that current is entering into dot and then inductor and leaving out.
Okay, sir.
Second branch also we should take the current in the similar way. Then only I can say the mutual impedance between these two is ZF.
Okay, sir.
J0.1, positive J0.1.
Yes, sir.
But if you take current in reverse direction, first branch we have taken first entering into dot and then leaving from inductor.
Yes, sir.
But the second branch you have taken first entering into inductor and then leaving from dot.
Okay,
Then
sir.
mutual linkages between these two will be opposite to the previous one.
First and second one mutual, sir.
Then
1 and
definitely
3.
you have the mutual linkages opposite to the previous one, right?
Okay, sir. Okay.
Then you should take Zm value negative. For example, in this problem, I have taken dots here in the problem. I have taken current direction in the similar way in the both branches. That's why I have taken this Zm value positive. Zm value positive J0.1.
Yes, sir.
For example, if you take the second branch current in opposite, then this Zm value we should take minus J0.1.
Yes, sir.
Getting?
Yes, sir. Yes, sir.
Yeah. Any other doubt you have?
Sir, previous problem, sir.
Tell me.
IA, IB, IC are given, sir. Phase B 0 sequence 0.1 at an angle of 0 degrees.
Okay.
IA is 1.1 at an angle 0 degrees, sir.
Okay.
And IC is 1 at an angle 120 degrees plus 0.1 per unit.
Okay.
Then option is given 4 options, sir. Which one is correct, sir?
Have you attempted it? Have you solved it?
Yeah, sir.
Have you solved that question?
Yes, sir. I got answer 3 point something.
You send me your solution to the Telegram now.
Okay, sir. Okay, sir.
Okay.
Okay, sir.
Send to me and come on. Okay.
Okay, sir.
Okay. Yogashri.
Sir?
Tell me.
Sir, Y bus is a diagonal is always
Always non-zero for a practical system. For example, Yogashri, if you take one network something like this is some node 1, node 2, node 3. Okay. And this is some reference 0. Something like this, we have some network.
Yes, sir.
And I connect one capacitor bank here. Okay, admittances I am giving all the elements admittances. This is minus J3 per unit, minus J1 per unit, minus J2 per unit. This admittance is plus J2. Then what is capital Y33?
Y33
0.
0.
This type of network may not exist practically. Okay.
నాది ఏంటంటే డౌట్ సార్,
Hmm.
ఇప్పుడు ఇంతకు ముందు లాస్ట్ పేజ్ లో కూడా మీరు ఏమన్నారు, y bus is ఆల్వేస్ నాన్ జీరో బట్ ఇట్ విల్ బి జీరో ఇన్ సమ్ టైమ్స్ అని అంటున్నారు కదా
Which value will become zero sometimes?
సార్. లాస్ట్ 97 పేజ్ లో మీరు ఒక మ్యాటర్ రాసి చెప్తున్నారు కదా సార్. Y bus జీరో ఆల్వేస్ నాన్ జీరో బట్ సమ్ టైమ్స్ ఇట్ విల్ బి జీరో అంటున్నారు కదా సార్.
No, I didn't said sometimes it will be zero. Diagonal, half diagonal elements may be zero sometime. Half diagonal, not the diagonal.
ఓకే
Diagonal will be always non-zero in a practical system.
ఓకే
Hmm.
సార్ మరి ఇప్పుడు y బస్ లో డయాగ్నల్ ఇప్పుడు మేము ఇప్పుడు y33 అనేది డయాగ్నల్ లోనే వచ్చింది కదా సార్, జీరో.
That's what I am saying you, Yogashri. For a practical power system network, always diagonal elements of the Y bus will be non-zero.
ఓకే
Okay. But in this network I have drawn on the paper where I am getting Y33 value 0.
ఎస్ సార్.
Okay. I am saying you this type of network may not exist practically.
ఓకే ఓకే సార్.
Okay. Understood?
ఓకే సార్, డయాగ్నల్ లో నాన్ జీరో ఉంటేనే ప్రాక్టికల్ గా అప్లికబుల్ ఉంటుంది, లేకపోతే అప్లికబుల్ కాదు అంటుంది.
Yeah.
ఓకే సార్. ఓకే సార్, అర్థమైంది.
That's it. Okay.
రైట్ సార్.
Sai Charan Reddy.
Hello, sir.
Tell me, Sai Charan.
Sir, that old and new admittances, that small y and capital Y, you took na, sir. Small y old is equals to minus of
Series
yes, sir, minus
compensation.
of capital Y. That I did not understand, sir. Yeah, yes, sir. Yes, sir. Series and shunt, both of them.
Okay. You tell me what's the slide number? Is this? Where you have doubt?
Sir,
At what point you have doubt?
in problem, sir. In problem,
In problem only. At what
At,
slide you have doubt? Sai Charan.
this one at somewhere you wrote that y12 is equals to minus of capital Y12, like that.
Y12.
Yes, sir. This one before page, sir.
This one. This one.
Yes, sir.
Tell me what's the doubt you have in this, Sai Charan?
You know this reason, sir. Why it comes at the time it was shocking, sir, to me. I did not understood this.
No, can you repeat again? I didn't listen to your question correctly. There's a noise.
I did not understand why y13 is equals to small minus y13.
That is from the definition of the Y bus elements itself. How to calculate half diagonal element in the Y bus? Sai Charan.
In
How
y
to calculate
in which
half diagonal element
changes,
in the
sir?
Y bus? Are you getting me? Are you getting my question? What I am asking? How to calculate half diagonal element of the Y bus? Half diagonal element is nothing but negative of the primitive admittance between the two branches.
Series admittance between two branches, no, sir?
That's what I have taken. Series admittance between the two branches is minus j 7.142. Negative of this number is capital Y13.
Here, which is primitive, sir? Y means primitive, sir. Primitive admittance means Y.
What is it? The definition?
Capital Y.
Capital Y is what? Capital Y is Y bus element.
Half diagonal element.
Capital Y is a symbol
Y
for
bus
Y
element.
bus
Half
element.
diagonal element. Yes, sir.
Small y is a symbol
sir.
for primitive admittance.
Okay.
Yes, sir. That notation I have followed throughout this chapter. By mistake, if you write anywhere small y, capital Y interchangingly, then definitely it will create a confusion. Okay.
Yes, sir.
Hmm.
Okay, sir. Okay, sir.
Clear?
At initial point only, I have this doubt, sir. Yes, sir. I was
Okay.
carrying
Have you
that doubt
attended
throughout the
starting
class.
slide of this day? Starting
Sir,
slide.
sir, when you are telling this, yes, sir. Yes, sir.
Starting slide have you attended?
Yes, sir. Yes, sir.
There I have mentioned no notation. Capital Y is a letter for Y bus element. Small y is a letter for primitive admittance. Similarly, capital Z is a letter for Z bus element. Small z is a letter for primitive impedance. We have to follow this notation
Okay, sir.
throughout this chapter. If you don't follow it, it will be confusing.
Okay, sir.
Okay?
Okay, sir.
Yeah.
Yes, sir.
Any other doubt you have, Sai Charan?
No, sir. No, sir.
సార్
Tell me, Yogesh.
సార్ ఇప్పుడు పోస్ట్ వేస్తున్నారు కదా సార్, అంటే నోటీస్ వచ్చింది కదా సార్ వేయమని.
Which one?
టీఎస్ ఇరిగేషన్ గ్రూప్స్ అవన్నీ పడుతున్నాయి కదా సార్. ఏఈకి కానీ ఏడబ్ల్యూకి కానీ అప్లై చేసుకుంటే ఇలాంటి మ్యాథమెటికల్ క్వశ్చన్స్ ఇస్తాడా సార్, లేకపోతే
Simple mathematical questions they will give. We are dealing this thing in the view of the GATE examination.
ఓకే సార్.
Anyway, already AP Genco was attached to GATE syllabus. GATE exam.
ఎస్ సార్.
AP Genco. Right?
ఓకే.
So,
ఇప్పుడు అంటే జెంకో ట్రాన్స్కో పడ్డప్పుడు మనం అప్లై చేసుకుంటాం కదా సార్ డైరెక్ట్ గా.
yeah, direct
సార్
problems they may not ask you.
సార్ మీ వాయిస్
Okay.
కట్ అవుతుంది సార్.
They may not ask big level of problems numerically.
ఓకే సార్.
Okay, they may ask small problems only, but concepts are needed. Whatever the concepts we are discussing, that will be needed for any exam. What is
అంటే
it
bit
Genco,
wise,
Transco or some other exam?
బిట్స్ లాగా వస్తాయి, ఇంకా ఫార్ములా బేస్డ్ లో క్యాలిక్యులేషన్స్ వస్తాయి అంటున్నారు అంతే.
Sometimes it may be formula based, sometimes it will be conceptual also.
ఓకే.
Okay, directly by using formula you may not get the answer sometime. We have to do some analysis. You should analyze that question, then only we are capable to get the answer.
ఓకే సార్.
Okay, so first you should be thorough in your what we call subject, then you can crack anything.
సార్ ఏమైనా బుక్స్ సజెస్ట్ చేస్తారా సార్ వీటికి?
You read these notes clearly, Vashri.
ఓకే సార్.
Better you read these notes and previous GATE problems, previous IES problems. These are what we call necessary, what I feel, rather than going for textbook and wasting your time.
ఓకే సార్.
Okay.
ఓకే సార్.
Yeah. Sarath.
Sir, good morning, sir.
Good morning. Tell me, Sarath.
Sir, in series and shunt capacitance, sir, in first question that they mentioned series admittance value minus J2 per unit.
Admittance.
Yes, sir. Shunt admittance.
Series admittance value, they said minus J2.
Yes, sir. Minus J2 means that is capacitance of the series in series.
Admittance minus J.
Sir, I'm having that confusion, sir. You have.
What is the inductor impedance? This is an inductor. Okay. What is the inductor impedance? JXL.
Yes, sir.
What is the admittance of the inductor? 1 by JXL. So it is minus J 1 by XL.
Yes, sir. Okay. Got
And
it.
if you have a capacitor, what is the impedance of capacitor? Minus JXC.
Yes, sir.
What is the admittance of capacitor? 1 by minus JXC, in the sense J 1 by XC.
Okay, sir.
Getting?
Yes, sir. Okay, got it, sir.
Yeah.
Thank you, sir.
Any other doubts? Please raise your hands. Any other doubts? Yeah, so I think nobody is having a doubt. Thank you. Bhaskar.
Hello, sir.
Tell me, Bhaskar.
Sir, by the equal area criteria, we can't say final stable point, sir.
No, we can't say final stable point, but we can expect it. We can guess it.
Okay.
Equal area criteria will tell you simply whether the system is stable or unstable. That's it.
Okay. But the waveform is swinging between the 2 points A and C.
That we are extending, right? That analysis we are extending.
Okay, okay, sir.
Okay.
Okay.
Hmm. Yeah, next class will be on Thursday, I think. Thursday, I think 17. 17. The day, is it 17 only or 15? Timing, it will be evening, they have announced. 15th of this month. 15th of this month. We have 5 p.m. to 9 p.m. F&S. Okay, and you have that induction machine class continued from tomorrow, today onwards. Yeah. So can I leave? Anybody having a doubt? Anybody having a doubt? Anybody have doubt? Please raise your hands. Sarath, do we have any doubt? Sarath?
Sir.
Sarath. Tell me, Sarath, do we have any doubt?
Yes, sir.
Tell
Sir,
me, tell me.
why we go for series and shunt compensation, sir? What was the need?
That we discuss in TND. It will come in TND. What's the purpose of that?
Okay, sir. Okay.
But as a problem we have solved here, but purpose we have not studied in this lecture.
Okay, sir.
Okay. Yeah. Pallavi. Pallavi.
In day 16, we solve one problem of critical clearing angle.
Okay.
In that case, you got answer 84.86, but I solved.
You correct it, Pallavi. Correct it, Pallavi. It's just a numerical, right?
Okay, okay, sir.
Correct
So,
it. If you are getting more than 100 or less than whatever it is, you correct it according to your calculation. Huh?
No, sir, I do more than more times, but I get not 84.86. I got 106.
That's okay. That's okay. That's what I am saying. You correct it if I
Okay,
committed
okay,
any
sir.
mistake. Huh?
Okay, sir.
Okay.
Yeah.
Because I will be following the answers given by the people in the Q&A.
Okay.
Okay. Fine.
Yeah.
Sridevi. Sridevi.
Sir, good
Tell me.
morning.
Good morning.
Sir, I'm having a little network issue over here. Just I want to know that today's class, what you have taken, that recorded video, when will I get to see, sir?
I think they may upload within 24 hours. Maybe tomorrow morning by 10 a.m. they will upload it.
Okay, tomorrow morning, sir.
Not tomorrow morning. Yes.
I have got a very serious network issue, so I missed.
Okay. You watch it. You watch it tomorrow.
Okay, sir. Thank you, sir.
Okay. Dwarkesh. Dwarkesh. Do you have any doubt, Dwarkesh? Yeah. Dwarkesh. Do you have any doubt, Dwarkesh? Yeah. So anybody having doubts? Can I leave? Anybody have doubts? I am unable to listen to you, Dwarkesh. You are making yourself unmute, but still I am unable to listen to you, what you are saying. Okay. So I think I can leave. Nobody might have a doubt. Thank you.